Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. Let's see. Anu, Maestran, Ginfuro, thank you guys so much for coming in. I'm no longer still working on the PhD. In fact, I finished that about a year and a half ago, almost. I mean, I finished it in December 2019. So it's been a significant amount of time since I finished the PhD. But I do want to talk about a little bit about research to start the stream off. So let's go ahead and, I don't know, go over here. Move that over there. Perfect. Okay, so we've got about 13 minutes or so. How do you pronounce it? If it's not Maestran. I don't understand how else you would pronounce it. I'm so sorry. Unless it said Maestrain on accident. Anyway, let's talk about it. So, as you guys know, I got my PhD in 2019, December 2019. I then worked at MIT for a year, and then I stopped working at MIT in January of 2020, and I've since been contracted with, a few different people to work on different things, but honestly, I should have been spending most of my time working on my own stuff. Now, during the PhD, I was really keen on this idea of Laos Labs. Essentially, doing research for in a way that is publicly accessible and understandable by a large group of people. That was the hope. But I never really made any progress towards that. And the reason I didn't make any progress towards it is simply because I just I haven't done any research for the past 2 years, So during the PhD, I started the PhD in 2014 and I ended it in 2019. I would argue that from 2014 to, we'll say 2017, I was just doing literature review. So I wasn't actually doing any real research, right? I was just learning things that I would need for research, right? Right. And then probably around 2018, I actually did research, right? But at the end of 2018, so 2018 to 2019, I was writing about research that I did, not actually doing the research. So during the PhD, there was really only like a golden age of like 1 or 2 weeks in the middle of 2018 where I was actually doing real research. And it sucks. I hate that so much because I actually genuinely enjoy doing research. And it's something I haven't been able to do. So then when I went to MIT, again, 2020, well, everyone knows 2020 was a bit of it was a mixed bag, right? And also, let me do this, so we have the push-up counter and stuff on the screen. But yeah, it was a bit of a mixed bag, right? So when I started working at MIT, I was anticipating it being a normal postdoc where you can spend a significant amount of your time doing research. Like the whole time throughout the PhD, I was really looking forward to the postdoc. But what ended up happening was when I joined MIT and I worked there, I didn't really do any research. I was basically just doing software development. Now, don't get me wrong, software development is still fun. I still enjoy it, but it just wasn't, it didn't feel right, Like, I've always had this, like, passion for research, for doing something that no one has ever done before, and MIT did not scratch that itch for me. Now, it could have been the specific job I was working at, it could have been a number of different things. And so, this idea of doing research for an open audience never really came to fruition because I kind of stopped doing research for the past 2 years. And so then I said, well, okay, let's just, try to figure out how to make the YouTube channel work, all this kind of stuff. And what ended up happening was we came about this project that was called Flamify. So the research that I do is somewhere in the middle between systems engineering and algorithm development. It's somewhere in the middle of these two things. It spans from computational, like computer vision, to computational sciences like physics and biology and stuff like that. It's a very broad spectrum of anything that could be considered kind of mathematical, but also like computational. Like anything that is computational mathematics kind of fits the umbrella of things that I enjoy doing. And I will say that during pretty much all of my PhD and all of MIT, and I talked about this a lot on stream, I was basically doing computational physics. And don't get me wrong, I like computational physics just as much as I like any other computational field, but I don't care about the physics, and I've never cared about the physics. I've always cared about the computational part of it. But of course, you can't really sell computation, right? So yesterday, when I was sitting back and looking at the Flamify package, I realized there's a lot of work that needs to go into making this package actually work, right? Like, we have a lot left to do. The idea with this package is that we take any image, and we turn it into a constituent set of fractal flames. So essentially, we turn any image into a set of fractals. Now, this is really cool for a number of reasons. Research-wise, is really cool because it means that we can take any image and we can turn it into a set of equations, which is super cool, and is actually the premise behind fractal compression, which is an idea of doing image compression in a very similar way. And so in this way, it's kind of like a new take on fractal compression. But it is definitely a new research field, something people haven't done before. And because of that, it's going to take a lot of work to care about that, to do that. So I got to thinking about how much work it would be. And yeah, I'll talk about that in just a second. You don't care about physics, you care about computation, but you don't consider software development to be research? Something doesn't add up? Yeah, that's right. So the thing is, software development is completely different than computational science, which is completely different than computer science, right? When I say I was doing software development, I mean that there was nothing novel about what I was doing. When I think about research, I think about pushing that boundary of human knowledge just a little bit forward towards a direction that people have never gone before, right? Even if it's something really, really stupid that people probably already know, just proving that that thing is true is still in itself research, is still in itself interesting, something that no one has ever done before. What I was doing in 2020 was not that. I was implementing methods that people had already created in a way that people have already done in a new software ecosystem. Now, there's still something interesting about that. It's still cool, but it's not that novel bit, right? People have done what I did before, and that feels bad to me. I want to be doing stuff that no one has ever done before. And yeah, I realize that I'm in a very privileged position to say that, but also, I spent the past 7 years doing nothing but, learning literature review, like getting to that stage where I can see that boundary of human knowledge and I know where to push. And so it's kind of a bit sad that I couldn't do it, and I wasn't allowed to do it during the end of the PhD, and during the postdoc. Hey, Janssen, how are you? So as I was thinking about Flamify and this idea of bringing images to fractals, right? What we have to do is, one, we have to implement the fractal flame method, which we already have. It's just a matter of kind of packaging it up. Then what we have to do is we have to kind of reverse engineer each image, and we have to find a way to take all of these fractal flames and put them together in such a way that it replicates the image. So this means we need some sort of optimization strategy. Optimization strategy. We'll just say strat. Okay. Now, in all of this, if you're going to do this fast, you probably want to like a fast iteration cycle. So this means you probably want to do some sort of GPU processing to make sure that the generation of your fractal flame is as fast as possible. Herein lies the problem. If we are doing the fractal flame method, essentially that means we have 37 fractal flames that we're going to try to replicate or like use in some sort of fashion in order to recreate an image. So you could have one that swirls the image around. You could have another one that creates a heart. You could have another one that does this and that. All these different flames all do different things. And the problem is each of these things has an affine transformation before and after. So that means each of these fractals, each of these individual flames is essentially a 12-dimensional space, because you've got the 6 affine transformations in and the 6 affine transformations out. So there's 6 little dials that you can manipulate. And if you have 37 of the flames, it's 37 as a random number, but if you have 37 flames, 12 per, you're talking about a 300 to 400 dimensional space that you have to traverse. So that in and of itself is a very complicated thing. So this optimization strategy is hard. I don't really know how to go through a very messy optimization path in like a 300 dimensional space. No idea how to do that. Then I started thinking about the GPU engineering. And again, I was stuck. I was like, wait a minute. Iterated function systems, which are the heart of the fractal flame method, they are iterated. They do one step at a time. Well, what is the one thing that GPUs can't do? Well, it's iterated things. You don't do that. It's in parallel, right? So the idea of taking something that is inherently a random and iterated process into something that is, well, not random, not iterated, something that you can parallelize is already a complicated task. And so when I was thinking about this, I had 2 options. My first option was like, you know what? This is a research problem. Let's just give up. Let's start moving ourselves towards things that will get clicks, things that people will definitely watch. Because in the end, what are we doing? We are just creating a weird fractal image filter. That's literally all we're doing with this project, but it's going to take months of engineering time, right? But then I thought about it a bit more, and I realized that, you know what? All of the projects that I've been interested in recently are things that push the boundary of human knowledge just a little bit in stupid ways. And it's stuff that I'm actually able to do now that I'm an independent researcher that I wasn't able to do in academia. All of this time that I spent doing computational physics when I didn't care about the physics and I didn't care about the paper out. I just wanted to do new algorithms and new methods, but I wasn't able to do that because I was so focused on the physics and I had to do the physics. I'm no longer constrained in what I can research. I'm no longer constrained by citation count. I'm no longer constrained by having some person above me. I can literally just do whatever research I want to do, so long as I can make it interesting enough that people will watch it. So I thought, why don't we just do that? And the concept, I don't exactly have it fleshed out yet, but it's like problem. That chotomate. The concept is problem of the X. I don't know what X is. X could be day, it could be week. I really don't know. I haven't figured out the time frame for this. Increase difficulty of the next set. All right, we'll do that. What is the next set? Arm hold? That's fine. Set, we should have increased difficulty in here somewhere. I think. All right, maybe if I just do, 1 second. And let's go over here. Increase. Okay, I don't have it. 1 second. Increase difficulty of the set. So that means we have to do, I don't know what it's going to be. What is that? That is 323 arm hold. That's fine. So that's the thing. I'm, Fulch just thinks weak is good. Gawabunga says my father would say that he traveled 372 dimensions to go to school when he was young. But yeah, so this is the idea. I just want to take this problem that is sufficiently interesting, that is sufficiently hard, but it's publishable, but it's not going to get a lot of citations. It's not going to do very much. It's just a matter of doing something that I find interesting. I don't care about citation count. I don't care about, getting some sort of incredibly novel thing that changes, how humans perceive reality. I'm not interested in that. All I'm interested in doing is creating a stupid fractal filter. And the way I see it is, if I'm going to create a stupid fractal filter, let's just kind of do it and create these, what are essentially, they're edited, but not super high quality videos, these more rough around the edges. This is the problem that we're talking about. Here's why it's interesting. Let's just jump into it type of thing. And so today is the first day that I'm trying that out. And the question that we have right now is why chaos games suck on GPUs. Now, I'm going to go on my little workout session for now. So we have 3 minutes and 30-second arm hold, which is admittedly a really, really weird, I don't like arm hold on stream because it's it's just hard to make that look appealing in any way. I'm just sitting there with my arms out. But we'll go ahead and do that. So we have 2 push-ups, I think 3 push-ups, and then 3 minutes and 30 seconds arm hold. And then we'll talk about the fractal images and all of that kind of stuff. Again, for those of you guys who have just come here, you haven't been to the stream before, really the concept is that we do a 5-minute exercise and then a full hour of some sort of project after that is started. So in the next hour, after we've done our little 5-minute workout, we're going to try to basically notate where we are with the fractal flame method and figure out what we need to do to really solve this problem of iterated function systems on GPUs. It's a lot harder than you might think, and it's just crazy. Gosh darn it. You're telling me my video and audio is out of sync. I just checked that. Every time I start stream, I always check that. Let me see. I always check video and audio before stream, so it looks fine on my end. Yeah, what's the issue? On my end, it looks fine. It sounds like there are 2 audio feeds. It's 0. Okay, there are 2 audio feeds. Well, no, there aren't 2 audio feeds. There's 1 audio feed. It's 0, 1. I can try to fix that, but I can't fix it during stream. I'm gonna have to turn off stream to do that if I'm gonna do that. But it's relatively close enough that I think it's fine. But the issue is that my mic audio comes from a different location than my camera audio. And so I have to sync them up. And every time before stream, I literally spend 10 to 15 minutes just getting the video and audio synced up. So when you tell me that it's not synced up, I get really pissed off. So it might be slightly off, but it should be close enough that no one legitimately should notice. I've closed streams before because the video and audio is out of sync. So anyway, I'm gonna go ahead, turn on the workout music. We're gonna go ahead and get that done. Music, and then yeah, we'll do that and we'll move on to the next bit. Let's do chill EDM. And yeah, so what I'm going to do is I'm going to move the mic. We're going to do the 3 push-ups and stuff like that. Also, Janssen, you told me to increase the difficulty twice, so we'll do that one more time. Increase difficulty, what does that give us? That gives us, I think there's like a print set. What did I call it? Print line. No, what did I call it? I don't remember what I called it, but what is it? It's going to be a, oh, I forgot to do, I know what I forgot to do. Set, reps here is equal to that. And then if we do reps, it should be 1 minute. What? And then we have to do it one more time, difficulty of 7. Ah, that's an error, so I have to add another push-up. 1 second. What's wrong? Set? Oh, what's happening? Ah, crap. I don't know what broke. Something broke, and I don't exactly know what broke. Yeah, I really don't know how that broke. It's for some reason telling me that the set is, I swear I had this working a second ago. Let me go over here. CD project swoleos. ls here, CD swoleos, ls vi readme. Where's the increase in, oh, okay. I think I see what happened. Let me see, what do I have here? Superset. The very top one is jumping squats. So where is the arm hold? It should be, 1 second. What do we have here? Rollouts legless. Wait, why are arm exercises here? They should be all the way down here. Okay, it doesn't matter. Let's just go with it. It's arm hold. We're gonna do 3 minutes 30 seconds arm hold, and we'll go from there. What do we have here? Methought I heard a voice cry, sleep no more. Macbeth does murder sleep. The innocent sleep. That knits. What are we talking about? The death of life. I break something with my code every day, almost. I try to automate stuff, but now it just takes more time. Yeah, I know exactly that feeling. Okay, I'm going to be right back. I'm going to change the microphone position. We're going to go down, do our workout, and then get started on the next set. So we have 1 more push-up, so that's what, 5 push-ups, I think? Totally fine. Yep, 5 push-ups. And give me just a second. Right, changing the microphone position, so I'll be out for just a second. Okay, looks good to me. Nice. Oh, I need to get chat. Okay, 1 second, guys. Let me turn on chat, and then we're good to go. Switch here. Where are we? Yep, good. So I have chat down here. Did I miss anything? Didn't finish reading Scottish Play. That's a mistake. Fair enough. Okay, so for those of you guys who might just be here for the first time, you've never been here before, it's a 5-minute exercise followed by a 55-minute project. I'm going to do 5 push-ups, and then we're going to do basically 3 minutes and 30 seconds arm hold. Anybody that wants to join along, you don't have to do all the push-ups, you don't have to do all the arm hold. The point is just to do some sort of exercise in basically 5 minutes before getting back to programming. So let's do the push-ups and go from there. All right. 1, 2, 3, 4, 5. Okay, so now 3 minutes and 30 seconds arm hold. Where's my, 1 second. Am I in frame? I think this is fine. Let me move the frame really quick. That'll do. Ugh. Okay, so I'm gonna do 3 minutes, 30 seconds arm hold. I'm just gonna keep track with my watch right here. So feel free to join along. Otherwise, just kind of hang out, chill. We'll get back to programming in like, 3-4 minutes. All right. I'm gonna go in 3, 2, 1, and go. Yeah, so with arm hold, I usually just, have the arms moving forward a bit, and then move it back. So every 30 seconds, I just go from arms moving forward to arms going back. For me in particular, I sometimes hit this left wall right over there. So I have to watch to make sure my fingers don't hit it. Yeah, we're definitely T-posing here. But for those following along at home, that has been about 25 seconds. It gets harder once you get to about a minute. So we're going to go back starting now. So again, it's 3 minutes 30 seconds because Janssen did increase the difficulty. They actually increased the difficulty twice, but I wasn't able to increase the difficulty a second time because I suck at and my code broke, so I just added another push-up. I'll try to figure out what happened there in a bit. So again, it does get harder as you go a bit longer. So since it's 3 minutes and 30 seconds and we have 5 minutes to do it, I'll probably just do the first 2 minutes. Then I'll take maybe a 30 seconds rest, and then I'll do the second minute and 30 seconds. So that's about a minute, so we have another minute till rest. So we're switching to move forward. But yeah, as far as the fractal flame method and all that's concerned, I'm actually genuinely looking forward to these kind of problem of the day. Just every single time I hit that wall, and like, it's always on stream, and then my finger's bleeding for the rest of the day. Just because I hit the wall. Oh my gosh. Okay, so 3 more seconds, 2, 1, and back. And then once we do the next 30 seconds, we're going to take just a 30 seconds rest, and then move on to the next bit. How bad's my finger bleeding? But I also always hate doing arm hold on stream, because it's just such a boring exercise to watch. Like, I don't know what I'm supposed to do. But it's okay. So for the next one, since it's going to be a minute 30 seconds, we'll do 2 45-second sets. 45 seconds forward, 45 seconds back. Those following along at home, just go ahead, give yourself a 30-second rest, and then we'll go from there. I'm going to look at my finger to make sure it's not cut too badly. It's fine. Janssen is dying. Well, to be fair, you know, like, if you're following along at home, I'll add the push-up when I get back to, the computer over there. Guess I'll die. So we have 10 seconds before going forward again. And then, again, it's going to be 45 seconds forward roll, and then 45 seconds backwards roll. So 3, 2, 1, and forward. But yeah, to be fair, like, I work out very regularly, like, every day. So the way I see it is, I mean, I don't know, like, I'm not saying I'm, like, super fit or anything, but what I am saying is that, you know, if you're not used to working out, some of these exercises might be quite hard for you. So you don't have to do, like, exactly what I'm doing. You know, you can do a little bit, or not even any of it. I used to do arm hold with weights added, so it's easy for me. Yeah, I usually would add weights, but I don't have any weights on me. So just kind of doing it free weight, and that's totally fine. Okay, 10 more seconds till we start rolling in the back. Let's see, 5 more seconds, and then we'll go back. And backwards. So this is the last bit, 45 more seconds, arm hold. And then we'll get back to programming, talking about the fractal flame method. Oh, you can see me down there in the little corner screen. Hello. Other hand, hello. That's fine. All right, 30 more seconds. And yeah. Also, like, I work my shoulders a lot, so arm hold's actually pretty easy for me as well. I probably should do it with weights. It's kind of just a go-to shoulder exercise. So, 15 more seconds. And then we'll just kind of get back to it. 10 more seconds. Have you tried holding your arms vertically upwards before? I can only do it like 3 minutes. Vertically upwards, like, wait 1 second, like this? We're done now, by the way. So, like, a streamline position. I'm gonna feel this tomorrow. Don't worry, we got a new exercise every top of the hour. But yeah, so I used to do this position all the time because I do, I swim, so streamline position is what I'm used to. Give me just a second. I'm going to pop back over to my computer, so be back in just 1 minute. Okay, give me just a second to fix everything else. I think if I do this, it should be fine. I'll be right back. Okay, good to go. What do we have here? Feels good? I'm happy to hear that. So, yeah, for those of you guys who just jumped in, let's see. So I did get an extra push-up while I was doing that, so let me fix that. Clear the push-up counter, add one to it. I'm going to change the music back to what it was before. And now I'm going to generate the next set. So I think we can do that with just set reps is going to be equal to cycle set. And the next one's going to be jumping squat, 55 jumping squats. Who? 55? Who came up with this one? I think I've actually never cycled onto jumping squats before. I think 55 is probably too many. So I'm actually going to just preemptively decrease the difficulty. So set is going to be equal to decrease difficulty on that one. And now let's just do, how do I print again? I just totally forgot. Let's go here, quit, cd into source swoleos. Oh, it's here. Vi source swoleos. And we got what? Output set. Does that also cycle? Oh, no, it cycles. Oh, no, it doesn't. Oh, that's the next set. So what if I do reps is going to be equal to select reps? Okay, 46. That's probably a bit better. Oh, no, did someone add difficulty? What do we have here? We decrease the difficulty, then we decrease the difficulty again. So now we can do it one more time. So that is hopefully doable now. How many reps do we have? 37. This is probably doable. Let's go for minus push-ups. What do we have? So we should have one more push-up. So let's go back to the push-up screen. And it should be 37 jumping squats, which is still a lot, and one push-up. We're okay. We don't have to... I'll decrease the difficulty again, but I think we're okay. We don't need to decrease it too much more, unless you guys are doing it at home and you guys are really trying to follow along. Okay, so now let's go on to the heart of today's stream. So we just talked a bit about what the idea is for the stream with the just problem of the day concept, where we just kind of hop into a problem and just unapologetically talk about some form of research that I do. You know, and so today we're going to talk about specifically iterated function systems and how they interact with GPUs, because this is actually way more complicated than, like, it's just more complicated than people think it is. Like, let's just start at the start. So what is an iterated function system? Iterated function system. Right. So I'm also not sure how I'm going to edit this, so I'll think about that later. But let's talk about what this is. So I do have a video on iterated function systems talking about what it is, why it works, and all of that kind of stuff. I'm going to start with probably the most stereotypical example of an iterated function system, which is known as the Sierpinski Triangle. I'm going to go ahead and pull up a visualization of that. So CD projects, simuleos, fractal, I believe. L is here, and I think we should already have a video, but maybe not. Maybe I haven't generated it. Let me do CD videos, algorithm archive, and then I'm looking for iterated function systems. L is here, and there should be a video in here. Sierpinski Hutchinson, MPV. Sierpinski Hutchinson.mp4. Okay, so here's the idea. Let's start with 3 points, A, B, and C. I think you can see all the points. I'm just covering chat, and that's 4. Okay, so we start with 3 points, A, B, and C, and then we create 3 new points, D, E, and F. What we're going to do is we're going to create a set of functions. One function will bring you halfway towards A, down here in the corner. Another will bring you halfway towards B, and another will bring you halfway towards C. What we can do is we can make it so each one of these points, D, E, and F, generate 3 children. Each of these children move according to one of those functions. So one child from D will move halfway towards A. One child from E will move halfway towards A. One child from F will move halfway towards A. And, you know, another child from each pair will move halfway towards B, and another child will move halfway towards C. And if we do this, we end up creating, you know, essentially subtriangles of subtriangles. And if you keep going along, you eventually start to create some sort of Sierpinski triangle shape. So this concept in here is known as an iterated function system. Essentially, as long as we have a set of functions that we are iterating through, no matter how we iterate through them, we can generate a some sort of fractal-like structure. Now, of course, it has to be a particular set of functions, and it has to be a particular, like, we have to make sure that we're going through the tree as, you know, fully as we can. But for the record, this is what we mean when we talk about iterated function systems. Just the idea of kind of going through 3 sets of functions in a way that, you know, allows us to generate the full structure of that function system. Now, the function system can also be called a Hutchinson operator or a bunch of other things, but for the most part, that's what we're talking about. Now, the way this is typically done is via something called a chaos game. So here, we're just going to go ahead and draw a Sierpinski triangle here. And I'm just going to pause it right as this little point in the center starts to draw. So the idea with this type of iterated function system, the way in which we are going through the iterated function system is via a random method. So what we do is we start with some random point, and then we say, okay, this random point is going to choose some random function between the three to move on to next. It could move to halfway towards C. It could move halfway towards B. It could move halfway towards A. It doesn't matter. It picks a random point, moves towards there. Then that point chooses another function. So now it's moving halfway towards A, then halfway towards C again, then halfway towards C again, then halfway towards A, then halfway towards B. And eventually you start to notice that this point migrates or finds itself on top of the Sierpinski triangle. Right here, you can kind of tell it's there. And as you move along further and further, you really can see that it's eventually generating these points on the triangle. And it's just going to hop around again and again and again until eventually it will generate the Sierpinski triangle shape. Now, let's talk about these two different methods to generate the Sierpinski triangle, right? So the first way we did this was via a tree, we'll say tree spanning method, right? A spanning method. Now, I have another video on how you do this tree spanning method. The idea is that you do a single point in space, and then you have each one follow one function. So this one follows function 1, this one follows function 2, this one follows function 3. Totally fine, super cool, works just fine. Then this generates 3 children, again follows function 1, function 2, and function 3. And this one follows 3 children, function 1, function 2, and function 3. And this guy follows 3 children, function 1, function 2, and function 3. And eventually what you're doing is you're creating this giant, like exponentially increasing problem. So one solution that we found that is, I think, particularly elegant is to count the trees or count the branches in this tree via a bijective trit space. So the idea is if you have a function and you have to go through all different branches of this, well, all we have to do is we say, well, this is function 1, 2, and 3. So if we want to apply function 1 to our point, we say 1. And then the next branch down here, for example, would be 1 and then 1 again. But for example, you could do 1, 2 to get to this branch, or 1, 3 to get to this branch, right? And so the idea is if you just kind of iterate through, so you have like, I kind of counted these wrong. Let me move these over this way. Control X, Control V, move this over here. Perfect. So you can do 1, 1, 1, 2, 1, 3, and then you can do 1 second, 2, 1, 2, 2, 2, 3. And you 3, 1, 3, 2, 3, 3. And by counting up in this way, we don't have to keep the data structure in memory. We can just kind of keep some sort of trit string, and then we know which functions to apply by parsing that trit string. That would also totally work. And that's kind of how we implemented the tree spanning method last time. So we didn't have this exponentially increasing memory. Instead, we only had a linearly increasing memory because we just had to increase our trit string by 1 element for each layer, right? Totally cool, works just fine, not a big deal. I remember in class last quarter, we generated it with that second method. Right, so now let's talk about the most common method, which is the chaos game, which is also the title of the stream. Isn't method also embarrassingly parallel? No, this method is very far from embarrassing. Wait, what method is embarrassingly parallel? Neither of these methods are anywhere close to being embarrassingly parallel. That's actually my point here. So, but I'll get to that in a second. So the next one is via the chaos game. Here you take some random point X. Maybe there is a way to do a tree spanning method embarrassingly parallel. I don't know of it. Tree spanning parallel. Parallel. Maybe there is. This actually might be something to look into. Yeah, let's talk about that in a bit. Run backwards from least to root in parallel. Does that work? So if you let's table that for now, and let's talk about it in just a second, because that actually might be the best way to go. But for the chaos game, what you typically do is you start with some point X, and then you choose a random function, function 1, function 2, function 3, right? And then after that, you have a new location, we'll call it X prime, and then it again chooses function 1, function 2, function 3. And because it's inherently iterative, it just means you have one point that's kind of moving around in space. Now, my point with both of these methods is that they don't work very well with GPUs, right? Neither of them are parallel. Now, my friend right here, might be right. There might be a way to do the spanning tree approach in a parallel way. I don't know that method right now. But what I will say is chaos games in particular suck on GPUs. And here's why, right? So when you think about a GPU, you think about a graphics processing unit. That is what a GPU is. The way the GPU functions is by basically doing a bunch of very small tasks very quickly. So, if you've got a screen, 1920 by 1080, that's your resolution of the screen. It's generating, what is that, 1 million pixels in essentially 1/60th of a second or whatever your refresh rate is. That's a lot of computation, but it's just kind of doing it all at once. It's doing it all in parallel. So the reason GPUs are faster for some tasks are because you can split that task up into little itty bitty parts that don't depend on other bits, right? So, for example, if we have a grid in space and this grid is composed of all of these different points, right? As long as these points are independent, the GPU works super well because, we could, for example, deal with the top 4 points independently of these 4 points over here. In that case, we can do everything in parallel. Nothing really matters. Now, the reason the chaos game sucks for GPUs is that it's iterative, right? So, for example, if this is the first point, and this is the second point, and this is the third point, we can't do the third point independent of the first and the second point. That's just not going to work, because that's just not how parallelization works. You can't parallelize things if they have to be done in a particular order. They can't be run at the same time if one depends on the next one, right? So this is why the chaos game is a particularly bad method for GPUs. So let's think about ways in which we could do this. So let's imagine a system where instead of having one point that's going through our function system, like just one point jumping around, like shown in this animation here, we have actually a dozen points or maybe 100 points that are all doing the same thing. Again, in that point, as long as we have like maybe 100 or 200 random points that are generated at the start, we can parallelize that. We can make each individual point go through the function system. So you might have, let's just say for the sake of the argument, we'll have 8 points here, right? So each of these is just going to go through, and it's going to go like maybe function 1 for this guy, function 3 for this one, function 2, function 1 again, function 2, I don't know, function 3. I'm pretending these are random, but clearly they're not. So these go through these functions here. I'm just going to draw it like this, the function 1. And in this way, yeah, you can parallelize a task. I missed one, but that's okay. You know what I'm saying. They just kind of go through each function. And this way you can parallelize it in a set of 8. This kind of works okay because you can still iterate through the function system and it will work fine. The big problem is how the GPU actually works. So the GPU is actually split into these things called warps. Now warps are basically the minimum level of functional execution. That is to say, if you want just a single point here, to have a single function applied to it, that actually will not work in a GPU because the minimum level of parallelism is 32 elements. Now this changes based on your architecture, I think, a bit, but for as a broad stroke, you can say that the GPU can only deal with 32 elements as its minimum number. It can't just do one thing; it has to do 32 things at once. So that means if it's going to do 32 things at once, well, this point, this application of function 1 here is not just applying function 1 to one point, it's applying function 1 to 32 points together, right? So in this way, this idea of kind of iterating through a function system by maybe creating a bunch of different points and then having them all have different functions applied to it still doesn't work, unless you also provide some sort of offset or do what a lot of people do, where they will actually have basically the 3 functions here, function 1, function 2, function 3, and then they have the array that they're reading in. So here's your array in here. And they segment the array into thirds, right? So then they say everything in this block will be applied to function 1. Everything in this block will be applied to function 2. Everything in this block will have function 3 applied to it. And then what they do is every iteration, they shuffle this array, right? So this means that if they shuffle the array, they no longer have to deal with the whole, warp thing, because now they can make it so 32 elements are, appropriately, different. Like every 32 elements are no longer stuck together in that way. So this is how you would typically implement an iterated function system on a GPU. And I think I've lost a few people, but if you have any questions, feel free to ask, because I think one big question people are going to ask is, well, okay, isn't this shuffle like really bad? And the answer is yes, the shuffle is really bad. Shuffling data on a GPU is going to be essentially, like, if you guys have heard me talk about GPUs before, you know that GPUs have like incredibly bad data I/O. Like copying data from one block in global memory to another block in global memory is incredibly slow. So this idea of just shuffling the array every iteration, though will work functionally, is still particularly slow for GPUs. So the question is, how do you solve this problem, right? Do you, one, do what Maestran is saying over here and say that maybe we try using a different approach, like, for example, the approach we had with this tree spanning method? Or do you try to find a way to maybe use some sort of weird shared memory accesses or something to do the shuffle in a more efficient way? The L2 cache on GPUs, right. That's so L2 cache. I think is the same as shared memory. I typically don't know, so I don't know CPU terminology so well. But for GPU terminology, you've got a global memory bank, a local memory bank on every thread, and then a shared memory bank between threads, which usually can hold a bit of space. So anyway, the question is, how do you solve this? And the answer is, I don't know. And this goes back to where we were just a second ago, when we were talking about maybe doing a problem of the day. Yeah, we're just unapologetically doing something that people haven't done before yet. Yeah, okay, they have done this before, right? This bit is kind of figured out. Like, for the most part, people leave it at this. In the literature, this is what I see people do. Just shuffle the array every time step, and that's just what they do. I say that's crap. I say we want to do a new method. And herein lies the problem that I was mentioning before. A lot of people in the literature, like, they need to get a project out, right? They need to solve a problem, and they need to publish that problem. So, dealing with shuffling of an array is not a problem that they want to solve, but it is a problem I want to solve. So we can go from there. And the tree spanning approach, though each node only depends on its parent, if you can enumerate the leaves, you can just let them all compute their paths through their parents with some duplicate computation. But who cares? Actually, I think you might be right about that. So what you're saying is journal new page before. Actually, this might be the best idea to go forward. I didn't even think about using the tree spanning approach. I was going to try to find a new way to do the chaos game approach. But I think you're right. I think we can just do we can try the tree spanning approach. So if I'm hearing Maestran correctly, and again, apparently I'm mispronouncing his name, the idea is, if we have, let's just draw 9 elements here. So what do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go through here and through here. 1 second, I'm bad at drawing. Okay, so what we're doing here is we start with some initial location x. It doesn't matter where x is, but we'll just say it starts with x, right? And if we go down this branch, we apply function 1. We go down this branch, it applies function 2. And we go down this branch, it applies function 3. And then up here is the same. Function 1, function 2, function 3, function 1, function 2, function 3, function 1, function 2, function 3. If I'm understanding correctly, what you're saying is we basically load the GPU with these guys here, okay? And then, since we know which paths they need to go on, what are we trying to do? So, okay, wait. We're trying to span the tree as effectively as possible. So we can go down n steps, where n is here, n is 2, I guess. So we could go down, let's say, 10 steps instead, right? And at 10 steps, what would that be? That would be 3 raised to the 10, which is a large number. 1 second. Let me close this up. CD project Simuleos. I'm just gonna run Julia. What is 3 raised to the 10? That seems huge. Oh, that's actually not so bad. That's 59049. So that's 59049 elements. We load all of these guys up in the GPU, and then we do some sort of work stealing method. Wait, I'm still trying to figure this out. Right, so like all the threads compute the root, but you split the threads evenly, computing the next level, so on until you have 1 thread per leaf. Oh, okay. Wait. Yes, that will work. That should work. I'm trying to think. Is that is that better or worse? It's you. The issue here is the memory, right? Because you still have to keep all of those points in memory then. And that's what I'm afraid of. So if we look at the memory footprint of that method, it's going to be 59049. You need to have a balanced tree. In this case, it's always going to be balanced, which is nice because of the way that we're counting. So, for example, in this case, we're counting through bijective trit space, which basically means that we will always have a balanced tree that we're moving through. So that's one nice advantage of going through iterative function systems in this way. But this does mean, unless I'm misunderstanding, that we have to queue 59049 elements to start, which is fine. How much is that? So if this is one... So you have n threads, each computing log n nodes in parallel, theoretically. So you have n threads, each computing log n nodes in parallel, theoretically. N threads log n... Wait, why is it log n nodes? I'm sorry, it's a stupid question, but I don't know if I understand that. So the memory footprint here is going to be this times probably 2 floats. So this is going to be times 64 times 2. What is that? 59049 times 64 times 2. And it's times 64 times 2. And then we want to divide that by 1,000. 1,024, sorry. Ah, crap, I screwed that up, didn't I? 59049 divided by 1024 is what we want. And that's going to give us 730 megabytes. So we could actually go much higher than that. Let's do 3 to the 12th. 3 raised to the 12. In there? Yeah, okay, we can keep going a bit. Let's 3 to the 15th. Okay, that's about the limit of my GPU memory, I think. Oh, unless I'm really bad at counting. This is kilobytes, actually. So actually we want to do this by megabytes, which is going to be squared. Yeah, no, that is the limit of my GPU memory. Right. Log n is the tree depth. Log 3 is the branching factor of 3. Oh, I see what you're saying. Right, so you're saying it's log n steps. So this here is a log n. Right. Sorry, I kind of suck at this type of stuff. I need to get better at it. So assuming you have 2 gigabytes of memory free on your GPU, you can definitely do that. What I'm trying to think about, though, is that we know where all the positions are, right? We already do. Like if you're going, what I'm suggesting is that each thread only keeps track of its own path from the root to the leaf. Right. Well, it only keeps track of its own path from the root to the leaf. So this is where I'm actually a bit... But that means the thread still has to keep some memory, right? Like, I think we're saying the same thing. I mean, if we're going to have, for example, if here we have 9 leaf nodes, that means you need 9 threads, right? Which is fine. But, you know, eventually you run into a memory limitation. Meanwhile, this other method here where you shuffle, though you do have to shuffle every time, it will noticeably be a small array that you're shuffling. Right? Because essentially... No, it shouldn't be. It should actually be a large array also. Never mind. That was dumb. I was thinking it'd be a small array, but no, it should be a large array. Yeah, so the problem with this method here where you're shuffling, the major issue is still going to be data I/O. Data I/O. Okay. In the triangle case, the thread needs to know its path, and it needs to know its current subtriangle it's working on. Why does it need to know the subtriangle? I don't think it needs to know the subtriangle. I think it just needs to know the path, right? Because, right, like in this case, essentially, like this function up here is just 0, 0 or 0, 1 or 0, 2 or something. But the threads themselves, can run parallel with serial. It makes no difference as each would compute its own path from scratch. Right. So I guess the question is, I'm gonna look up this parallel spanning tree stuff. Maybe I'm like, again, this is stuff that I don't know and I should. Am I wrong to say, what is a minimum spanning tree? A minimum spanning tree, or minimum weight spanning tree, is a subset of the edges of a connected, edge-weighted, undirected graph that connects all the vertices together without any cycles and with a minimal possible total weight. That is, it is a spanning tree whose sum of edge weights is as small as possible. Are we really going to go that low level? I think so, yeah. I mean, why not? The question is, you know, we can do so we know that the chaos games themselves are bad. Like, we know this method sucks. So the question is there a way to do it better, potentially via the graph theory approach? I don't know, maybe, right? I mean, again, before we showed that if you just iterate through the trit strings, you can actually find all possible locations of, all possible locations within the Sierpinski Triangle, right? So essentially all we're doing, we're not going through a huge 2 or 3 n-dimensional space. We're actually going through an n-element string, right? And so the question is, can we iterate through all possible locations in the n-element string better than we can iterate through all locations in the oh, that's actually correct. That's an idea. I like that idea a lot. Thanks, guys. I mean, I don't know if that's workable in practice, but it seems like the first thing I'd try to understand the problem, which is not given. Okay. So here's what we have here, right? So we have an n-element trit string. I'm just going to say, it doesn't matter. We're going to say 0, 1, 2, 1, 2, 0, 0, 1, 2, 2, 2, 1, whatever. It doesn't matter what the trit string is. But this is a way in which we traverse through the tree. This is a way in which we traverse through and create our iterated function system. This is the same as saying that we started with some location x, and it applied 0, 1, 2, 1, 2. So it applied these functions in order to get to that location, right? It's the same as saying that. So the question is, what if instead of iterating through points, we just kind of randomly shuffle these guys, right? So what we can do is we have a set of trit strings that are n elements long. And then what we want to do is we want to basically just find a systematic way to modify this string to basically go through as much of the function system as possible while using a minimum amount of energy. I think, or not energy, minimum amount of data. I think this is close. We're really close. And you can compute any number of such strings in parallel. Right. I think that's what we want, right? Because we just queue as many of these strings up, and then we can just kind of mess around with them. That's it. That's what we might want to do. I like that. That's really cool. Okay, so what are we doing with this? Good question. Thank you for that. Because I tend to get sidetracked, and I figure, if people ask, what are you doing? I think it's a good time to talk about what we're doing. So let me CD into projects, Flamify over here, ls. And let me just do Mirage. I don't remember where I kept these images, but here's one image known as a fractal flame method. It's a combination of a bunch of different fractal Lie patterns put together. So essentially this concept of the iterated function system, where you take 3 functions and you iterate through them, function 1, function 2, function 3, function 1, function 2, function 3, is a way in order for you to create something like the Sierpinski Triangle, but also other structures. Like, for example, you could generate just a bunch of weird things. And so what the fractal flame method does is it combines a bunch of these iterated function systems together, along with affine transformations, such that you can create these, I would say, relatively pretty patterns, right? And there's a bunch of different ways to do this, and we're kind of moving one step at a time towards this direction, right? So what we're trying to do with this particular project is the opposite of fractal compression in a way. What we're trying to do is we're trying to take any image and turn it into a constituent set of fractals. Now, that is actually kind of the same thing that fractal compression does, but we want to use the fractal flame method instead of doing instead of using fractal compression, which has more of a limited set. And so this is kind of the idea that we have. I'm not entirely clear on this movement computation for this, but if we're working with 2D points, can't you have each function be some sort of matrix transform, and then each trit string is just the product of those transforms in that order? Yeah, that's essentially what the trit string is, right? It's just we don't know which function That is exactly what that trit string is. That's what it is. It's just a way for us to count through that space, and then we create a transform and apply it. And that's the idea. To get a bunch of random points on the triangle, take a bunch of random integers and encode them in base 3 to get the path. I need to think about that one a bit. GPUs can do matrix multiplication pretty quickly. Yeah, definitely. This is actually why the trit string thing might actually be a good idea. I'm actually like, I was not thinking about going down that route today, but I'm pretty excited that people thought about that. Like, that's actually something that this is good. We're moving forward, like, in some direction. So what is this? This is a set of 3 different function systems put together. There's one for a heart that you can kind of see here if you look at the outline. Then you have another sinusoidal, which creates the eye pattern. And there's a few more put together. Each flame has its own color associated with it. So like the heart was, I think, pink, and then the sinusoidal one was, I don't remember. There were some colors that made white when you put them together, and all this kind of stuff. But the point is, you can create these interesting patterns with these function systems, right? And so the question is, can you combine these function systems in such a way to recreate an image? And if you can, how do you do that? And the answer is yes, you definitely can. Like, Fractal Compression does this all the time. Literally, it's just a process of turning an image into a set of fractals. That's what Fractal Compression is. The question is, like, can we also do this with the fractal flame method? Can we do this to make, like, I don't know. I just don't know. This is where I'm at. Like, I know this is a lossy compression method. The question is this lossy compression method a more advanced or kind of worse version of fractal compression? That's kind of my question, and I don't know. Okay, but so far, I'm actually really excited. Like, really excited. You guys, I mean, this idea of, I was going to do some sort of really tricky systems engineering approach to get the iterated function system to work. But I think you're right. If we load our GPU with, how are we going to do this? So, okay, what this turns into is essentially some sort of matrix transform. Matrix transform. Right? Totally fine. So it turns into a matrix transform. So that's easy to do on the GPU. You can literally just encode, like, if you have n elements coming in, you multiply with trit string. We still run into the warp problem. But I think that can be solved by doing the following. So we still have the warp problem, right? And for those of you guys who just jumped in, the warp problem is that the GPU's minimum level of, I guess you could say, not parallelism, but minimum level of serialism, the minimum number of elements it can access at any point in time to perform an operation is 32. So what we could do is we could have 32 random points. I think this is still fine. I think what will end up happening is, okay, so we still have to figure out that warp problem. Okay, that's still a problem to figure out with the application of the trit string. But I'm fairly confident that this can be done in parallel. And so if we have m trit strings to apply, right, so if you have m strings to apply, how do we, the generation of those m strings can also be done in parallel. And I think that's also pretty good, but again, we still run into the warp problem here, which is the reason why they had to shuffle. Let's see. What is this? Is this like the Fourier transform system of image compression? I think it's slightly different. The way that the fractal compression works is, in fact, let's just look at that in just a second. The trit string is the same as a string of digits of given integers in base 3, correct? So if you really need one integer per string, then you just extract base 3 digits with modulo division. If you really need one integer per string, we need one float per string, I think, unless I'm wrong about that. Oh, no, I see what you're saying. Right, the trit string is actually, yeah, so we can't use, we cannot use, like, we can't just use an integer for that. You have to apply the functions in at least 32 at once. Correct. Well, rather, no, it's kind of the opposite of, well, okay, just to be clear, because I'm not sure, that could go either way. you have to apply the functions to a set of 32 elements at once. So, for example, if you had, let's say, 128 input values, then you'd have to split this into a group of 4. And basically all of these guys would be applied to this one string, and all of these guys would be applied to another string, and so on and so forth. So the minimum number of elements you can work on at once is 32. Which is, that's the big problem here. That's why you have to shuffle the array. Because if you don't shuffle the array, you're going to run into a problem in that, yeah, you're stuck. The 32 elements are always going to be coupled next to each other. Okay, I think I want to just take a brief jump into the fractal compression because we've been talking about it a lot. And this is something I misspelled compression, but hopefully, there we go. And let's just read about it, figure it out, and go from there, because I think it's super similar, and I think we're just right on the cusp of talking about it. Time for groceries. Hopefully my ideas didn't put you completely on the wrong path. No, I appreciate it. This was actually really good. Also, guys, again, we're trying something new with Stream where we just unapologetically do things that are like very, very close to the boundary of human knowledge. And again, I say that in like a very weird way. I don't mean that in like some sort of, what we're doing right now is a problem that no one cared to solve because there wasn't funding to solve it, right? Like, but at the same time, it's interesting, and I think, I don't know, we're just trying to see if people are actually interested in solving kind of difficult problems together, and that's where we're at. So I think what we need to do is look at fractal compression, see how it relates to what we're doing right now, and then kind of go back to it and see if there's lessons here. Okay, we also not only need to look at fractal compression, but we also want to look at parallel fractal compression. Fractal compression. Now, I do know that fractal compression is lossy. You will lose some sort of information, which is great. We actually want to lose information. In our case, because we're trying to create a fractal filter, we actually kind of want to lose a little bit of information to make it so our new fractal image doesn't look exactly like our old fractal image, or like our old image, right? Because in some sense, we are trying to make something that's like a clicky video in the end. And so if, for example, we have some image in, right? And we get the exact same image out, there's good and bad. Good from a science perspective, because it's like, wow, look at that. Our fractal compression method is better than the normal fractal compression methods. But it's bad in the sense that people are not going to click on the video if the before and after images look identical. You know what I mean? So let's go here. Let me read this. What do we have? Okay. So I think, yeah, let's just kind of queue up things that we're looking for. And then we'll do the next workout set, and then we'll come back. And I think the next hour, we're just going to hone in on fractal compression. That's what we're going to look at, I think. Why did I do that? Okay. Survey of parallel algorithms for fractal compression. Oh, this is perfect. This is exactly what we want. Great. So let's go ahead and, I hate that this opened up in, okay, let me move this to another directory really quick. So I'm going to just go over here. I'm in the flamify.jl package. L is here. I'm going to make a directory for notes. Why am I dumb? Hey, Janssen, how many times did you decrease the difficulty? 3 times? Oh, so we have 4 decreases in difficulty. Let me see. What do we have here? We need to... 4 decreases in difficulty. I mean, we're at difficulty of 1, so we have 10. We have 10 jumping squats to do, which is fine. It's totally fine. You did it 2 times. No, you have 3 decreased difficulties put together, and I only decreased it 3 times in total. But Anu also decreased it once. So we had 4 decreases in difficulty. So we're at the lowest difficulty we can go here, which is 10 jump squats, which is perfect. Because 55 jump squats, which is what it was at initially, was way too high. All right. Let me move this over. What was it called? I want to, I'm going to open up notes. What does it say here? Heart function does not seem to work. Need to properly implement affine transforms. Let me just move this somewhere. Move notes into notes.txt. Perfect. Make directory. Notes. CD into notes. Move notes.txt here. And now we're going to move, what was the file you just sent me? The file you sent me was Peter Jimek. Peter. Peter. All right, Peter Jimek 3 here. Okay, so we've got the notes to look at. I think we're going to go ahead and do the push-ups, which do we even have? We have one push-up. I mean, go ahead and give me another push-up. Totally fine with that. So we'll do the workout, and then we're going to come back, and we're literally just going to spend an hour just talking about fractal compression. That's what we're going to do, because I want to learn about fractal compression and see how it's related to this topic. I still think this idea of iterating through a trit string is a really good idea. So there's definitely a way to make this work. And also, guys, I'm very interested to hear what you guys think about this stream. It is different than my normal streams in that I'm not, like, we're just kind of attacking a problem. My idea, again, of problem of the day is almost certainly not going to work. I like, there's no way we're going to solve this problem by the end of the day, but we're going to do our best to get as far as we can. And probably a problem of the week type of thing is more accurate. Like, I think we can probably make like a really decent go at this by the end of the week. So the problem of the week for this week is why chaos games suck on GPUs and how to fix it. And yeah, I think that's what we'll do. Cool. So let's go ahead and move on to the workout bit of the stream. We just have 2 push-ups and how many? It says 19 jumping squats. Let me see. Reps. 19. We'll do 19 jumping squats. That seems fine. What happens if we? It's fine. 19 is totally fine. Unfortunately, I've been playing a video game, so I only listened partially. Totally fine. Thanks for being here. But yeah, if you guys are interested in continuing these more research-heavy streams, let me know, because I'm very interested to hear what you guys have to say about this type of content. Like, I think, I mean, just to ramble for 5 more minutes, I do apologize for that. I think this idea of doing research publicly is something that people haven't done before, right? Like, it's just for a number of reasons, right? Like, you know, if you start here, if this is where you're at the end of high school, by the time you finish university, you know, you've got a pretty big avocado shape knowledge where, like, you know a bit more about math or something like that, right? And by the time you finish your PhD, you know, presumably, if this is the boundary of human knowledge, you know, wherever that boundary is, something like this, you've extended your own knowledge to the point that, you know, you still have all the stuff that you used to know, but you've kind of just barely blipped the surface here. And you've just pushed open that boundary a little bit. Getting people from here to here is super hard, right? And it's something that not very many people do. This is where science communication comes in. Science, right? And the issue with that is science communication is great, but a lot of times it simplifies the problem so much, because even the people doing the science communication have not adequately gone gone from through the gap, you know? So they do their best, but sometimes they miss the point. And so what I'm trying to say here is this idea of literally just unapologetically being on this boundary and just like, hey, this is something new. This is something people don't know about, and here's what it's at. It's something that I have never seen on YouTube. You know, you see it sometimes with lectures, but you don't see it like, you don't see people doing research in a way that's just like, oh, this is super cool. Like, you don't see people just like unapologetically being like, hey, this is a super cool thing, let's talk about it. And then just going straight into the technobabble, right? And that's kind of what I want to do. Thanks for the push-up, adding the push-up. And XX Mario, XX123136, thank you so much for following, really appreciate it. Okay, so now we're going to go ahead and do the next set. And again, next hour, we're going to jump right into the topic of fractal compression and just see where we go. Yeah, give me just a second. Oh, I need to change the music. I forgot about that. So we need to turn this off, turn this on. Perfect. Be right back. Hi, my name is Mario. I don't speak English. Could you help me recover my Facebook account? I cannot. I'm sorry. Okay, so how many push-ups is it? It is 2 push-ups and then 19 jumping squats. We don't do that kind of work here? Yeah. Okay. Oh, what am I doing? Screw it. Doesn't matter. Alright, 2 push-ups, 19 jumping squats. Let's go. Oh, gonna love this one. Alright, 1, 2, and it is just 2. Yeah, it's just 2. And now for the jumping squats. I'm actually gonna move the I'm gonna move the microphone, so you might hear just a little bit of a ding No, okay, let me... No, I got this. Okay, so let's do the jumping squats. We have 19 of them, so I'm just going to do a set of... We'll do 2 sets of 10. That's what we'll do. Okay. Oh, I just snapped my watch. And let me move this over a bit. I think that's fine. Perfect. Okay, so my jumping squat technique sucks. I don't really know how to do it, so we're just going to try it. There was a chemist on YouTube that wanted to create a non-proprietary formula for like antibiotic or something. It was very interesting. Cool. Yeah, it's something like that. Yeah, everyone was slacking today. That's basically where we're at. Okay, so jumping squats. I actually can't lift my arms all the way up. There's my stomach. I can't lift my arms all the way up, so I'm gonna do like bunny hops, and you guys are just gonna have to deal with that, and I'm sorry about that. So let's just go ahead and go. So 2 sets of 10 is what I'm gonna do. Feel free to join if you want to. Again, it's gonna be just do something. You don't have to do anything, like, you don't have to do jumping squats. Just kind of hang out, maybe get the blood flowing, that type of stuff. That's where we're at. Okay, I'm just gonna go ahead and go. It should be relatively easy, I think. I have no idea. Let's just go. I don't know where to. Let's just do this. All right, perfect. Yeah. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 more. Oh, that's actually pretty fun. I like doing those. Those are super fun. I never do them when I actually don't. When I select my own exercises, I kind of skip the jumping squats for some reason. But yeah, we have one more set of 10. Give me just about 10 more seconds of rest, and then we'll go ahead and hop into that one. Hop, because jumping squats. Ha! That's dumb. Okay, 1 second. Next set of 10 in 3, 2, 1, and go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let me move the microphone and we'll get back to programming. One second. Where do I put this? Oh. Am I in camera? Yeah, that'll work. Move over here, turn off the music. Okay, my breath, I don't have any breath. Oh gosh. That was harder than I thought it would be. Let me get some water. It was only 20. Yeah, whoever set the jumping squat difficulty really screwed up. Let me drop it a little bit. I think 10 at the bottom is fine. What do we have here? Let me go ahead and generate the next set. So I'm going to also drop the push-ups to 0 and do cycle set, decline push-ups. Okay, so now we're going to do VI. What am I doing? VI exercises, and then we want to go into legs. Take a look at jumping squats. Let's drop that down to 80 at the most. In fact, maybe even lower. Let's do 60. Yeah, that's probably about right. Oh, I don't know. We'll see. My USB-C audio adapter keeps on trying to activate voice assistant and randomly turns the volume all the way up. Man, I wish phones still had audio jacks these days. I don't have a phone, so I don't have any problems with that. That is your solution. Just don't have a phone. Okay. So let's go ahead and hop into fractal compression first on Wikipedia, and then we're going to hop into fractal compression on via the article that we were given. I don't know where the article came from. I don't, you know. Oh, I'll add another push-up. Great. Also, the boldness of XX Mario That is, that's pretty bold. Just to like hop onto a random programming stream and be like, hey, can you help me recover my Facebook account? I don't speak any English. Like, to a clearly English speaking science and tech audience. Like, that's pretty bold. You know? All right, let me get some water. I will make one more comment on the whole, he's desperate? I guess so. I don't even have a Facebook, so like I'm the worst person to ask. I'm gonna make one more comment on this weird avocado drawing that I had before. And that is the following. Okay. 5 years ago, when I started my channel, like I really started making mathematical concept with, you know, the what is an eigenvector video, and I really did try to like make content that is, you know, closer to that boundary of human knowledge. I got basically to this blue boundary. That's where I got to last time. There's a blue boundary in here, the end of undergraduate. And I just didn't feel comfortable pushing past that. But nowadays we have other channels like, you know, 3 Blue and Brown, and even a lot of other channels like, you know, Code Parade and stuff like this that really do at least get to this red boundary, right? They're not quite at the boundary, but they're so close. They're so close. And I think, you know, screw it. Let's just unapologetically, you know, just break through. Like, that's where I'm at. I feel like, you know, we're at the stage, we can just do it. And let's just do it. And so, as we hop into this kind of like complicated stuff, I'm asking if you have any questions, comments, concerns, ideas, anything like that, let me know. I will totally address it as soon as I see it in chat. But there is a caveat here in that, like, I'm not going to try to dumb down things. I'm going to try and make it as understandable as possible, but I'm not going to try to make it so simple that people, like, you know, that it loses substance, right? And that's what I'm trying to do. I'm trying to like give the fastest path from essentially the end of high school to the place where we're doing that research, right? And that's my goal, right? So I'm going to be trying to do that for the next few streams. We're going to see where we go. And yeah, that's essentially what I'm trying to do. Okay, so now it's good to just kind of take a look at fractal compression, see what we can do there, and really like try to understand it from a new, like, more intuitive level. So also, I just want to say before continuing, my very last video on YouTube did like super poorly, like worse than any other video I've ever put on the channel. And it was like really disappointing for like a few days. I was like, man, like that's just, I'm going to ramble for just one more second. Sorry about that. Then we'll move on to fractal compression. Like what I kind of realized was like, you know, the video I put out, I spent like a full week editing. Like I spent a lot of time. It was by far the hardest video I had ever edited. And yeah, you could argue there's some issues with it, but the past 3 videos have been like super like high in terms of editing time. It took a long time to edit these videos. But they performed no better than videos that were just clips of my Twitch stream. So I don't know what to say about that. YouTube.com user LEIOSOS. Shut up. There's Bob Ross. But yeah, this is the URL. But yeah, it was actually on the workout software that we created and stuff like that. But my point is that I understand that maybe the topic wasn't particularly interesting to people. But I think what actually happened was when I put up the video, a lot of people unsubscribed because they just didn't like that type of content. And that's fine. I forgot the H. My bad. That should be an appropriate link. Maybe the previous one worked as well. Whatever, it doesn't matter. Why does changing magnetic flux create current in the relativistic point of view? That is a good question that I used to know an answer to, but I don't actually have an answer anymore to it. I don't remember my ENM. Basically what happened was I've lost about 100 subscribers. So I have 75,000 subscribers, right? And I lost about 100 subscribers from the last video, right? So in the grand scheme of things, that's not a huge number. Like that is less than 1%. Like it's 0.07% or something like that. It's such a small number. But the number of subscribers I get per day is like 20 to 30. So it was basically 2 or 3 days of just not getting subscribers after putting out the next video. And I think what happened was, as people were unsubscribing, and as my own community was not clicking on the video, YouTube just didn't let other people see the video. Like the people who watched it generally liked it. And yeah, like the thing I liked about that video was, you know, sure, you could argue that maybe the editing wasn't as good as it could have been and stuff like that. But I think it's cool that we provided a software demo. You know, we did a whole bunch of really cool things in that video. That was the first for the channel. And I want to continue doing that. I want to continue doing things that people haven't seen before. That's what I want to push towards. And this idea, again, doing research on stream, doing research in the videos, I think that's genuinely where I want to go with this. Like this concept of being an independent researcher and just unapologetically just doing that stuff is just, that's what I want to do. And I think, you know, the faster we get to that stage, the better. And you're gonna have to push through some crappy videos to get there. Like, that's just how it is. You're gonna have to push through, you know, the beginning, the fledgling, the just crappy stuff that you start with. No matter what, the first time you do something, it's gonna be crap. But the more you iterate, the better you do. The more you try this one thing, the better you will get at that thing. And so, screw it. I don't care. It's pretty obvious why people dislike the video, because it's really different from what the usual content of the channel is. I don't think it was actually that different. I just think people thought it was different. Decrease difficulty of next set. Everyone's decreasing it. Oh, that's fine. I don't mind. So the next one, decrease difficulty. So now, what is that going to be? That's going to be... let me put the... I forgot. I have a different keybind now that I need to remember to press to. So we have the push-ups and everything on screen. Okay, that's it for the ramble session. I'm sorry, I should really stop doing the ramble sessions. I just do them too much. And yeah, that's where I'm at. So I think doing like my whole point with that story is saying that doing a project of the week type of thing, yeah, the editing is going to maybe take a hit. It won't be as well edited as the videos that I put out. But I don't think people care about the editing as much as they care about the story. And I think as long as the story's good, and the story is going to be good, I think it's fine. It's because we enjoy the Fractal talk. Decreased difficulty means more time for it. That's fair as well. Okay, so now we're going to hop into the Fractal Compression discussion. We're going to start with the Wikipedia article, and then after that, we're going to hop into the other article that people gave. Your content is hard science, which requires very curious and motivated viewers. The success of math YouTubers is an enigma. That's exactly what I'm trying to figure out. Like, how is 3 Blue 1 Brown so popular? Like, he's popular, don't get me wrong, and his videos are great. But like, I have a PhD. Of course, I'm going to think the videos are great. How is he doing so well outside? And also, why is my #1 video, Understanding 4D the Tesseract, why does it have almost 4 million views now and an insanely high click-through rate? Like, that one I was just unapologetically like, here's some linear algebra. And people were like, yeah, okay, that's fine. You know, I'm sure there are a lot of subscribers. A lot of subscribers are math, computer science students looking for educational content related to their studies. That's definitely true. In fact, I know that's true. Some of my highest viewed videos are, what is an eigenvector? What is a determinant? What are affine transformations? Is going to be one of those bigger videos, you know? Because people find my channel via Google search. Like, they find it when they're looking. What is what is 4D, for example? And I provide these videos in 5 minutes or less, and say, this is a way to understand it. People click on all things with 4D in them. Yeah, that's true. The comment section for that one's kind of a bit... I don't know the right way to say it, but most of them are saying things really stupid. Like, they're saying things like, you know, the 4th dimension is God or something like that. And I'm like, look, man, like, the discussion of the 4th dimension being time in Minkowski space, I'll agree with that. You can definitely see the 4th dimension as time in that, in theoretical physics. Totally fine with that. But saying that the 4th dimension is God, like, that's a step beyond, like, where I'm comfortable saying, you know, it's a step beyond where I feel you can adequately, you know, reason about the topic. I hit the microphone, and I'm sorry. Okay, fractal compression. This hour is all about fractal compression. We're going to read about it, learn about it, figure out how it works, and go from there. Okay. Just need to make a video title, working out in 4D. Yeah, I mean, the thing is, a lot of my topics recently have been on this boundary of, like, you know, like exercise and like athleticism and algorithm. Like, for example, I have the other idea of a heartbeat programming language. The idea here, like, basically we're taking an esoteric language, not brainfuck, another esoteric language, and we're just like making it so, you know, if you have a high heartbeat, you can encode a particular character or something like that. The idea is you run around a track and you encode, you know, Hello World is written basically at the gym. It's really cool, and I really want to do it. And it's like, look, no one's going to click on that video unless I have some videos before it showing that, like, hey, maybe we can do some workout stuff on this channel as well. You could even not technically lie by talking about the configuration spaces. That's fair. I'm really interested. It sounds like a fun disaster. That's the thing. Like, I've been coming up with all of these like stupidly fun disasters. Right. That's what I'm thinking as well. It's like, I like the tagline would be like, you know, are you a programmer who's always on the run? We have a programming language just for you. I think this will not click with people. Right. For me, I'm like, this is really cool. For other people, they're like, I don't think anyone's going to click on that. But like, I would definitely click on a video on that. Like if someone was like, you know, I made a programming language based on heartbeat, I'd be like, I'd click on that in a heartbeat. Yeah, that was supposed to be a joke. It was a forced pun. Deal with it. Next April 1st video, I don't think they should be on April 1st. Like this is a good video. Like it's really cool. I'm really excited to do it. And like this topic right here, like the topic for the video that we're working on is becoming a fractal. Becoming a fractal. And like, yeah, I don't know. Like, will people actually click on this video? I don't think so. Unless we get like a really, really cool image out of it, which is why I want to show like all the details going into it as well, and show that these are interesting problems that people are solving, and these are interesting things to talk about as well. Because if you just kind of consistently leave the interesting parts out of the videos, which is what I have been doing up until this point, I can understand why people aren't clicking, right? Like for example, I would click on, I don't know, I click on a video for two reasons, right? One video, I click on one video because, how am I saying this? What is an eigenvector? I will not click on that video because I already know what an eigenvector is, right? So that video is only getting new people who have never heard of this topic before. But what you want is a video that will get new people who are just going to look at becoming a fractal and be like, this is interesting. And old people, or like seasoned professionals who know this topic pretty well, right? Let's say Brainfuck is pretty popular, 335 views, definitely popular, right? Like that's the thing. Anyway, I also have other video ideas, like a bunch of videos. So the one I'm working on right now is this one. One that I'm really excited to do, but I think people probably won't click on, is coding a quilt. I'm excited for this one, like super excited for coding a quilt. I already have the quilt ready to go. I just have to sew it together. Like I have all the fabrics ready to go. I think it's really cool. Like I'm really excited for it. But like when we did it on stream, people were kind of like iffy on it. And you can kind of tell how well something's going to do on YouTube based on how well it does on Twitch. You know, like for example, if I get an average of like 10 viewers, I know that video is not going to do very well on YouTube. But if I get like an average of like, you know, 50 to 100 viewers, I'm like, yeah, this video will probably do pretty well on YouTube. So like, for example, I have another one on ray tracing planned, which, you never, here's my video on ray tracing. You're gonna, I don't know, Durer's door. I want to build this. 1 second. I want to build the world's first ray tracer. Gosh darn it, why? There we go. I can't use, oh, actually, did they already build? No, maybe not. I just wanted to see Durer's door. Come on, door. Where is Durer's door? Okay, let's just go to ray tracing. 1 second. Ray tracing, Wikipedia. There we are. Gosh darn it. There we go. And then we go here. It's literally just, it is the world's first ray tracing. Like world's first ray tracer, right? So I think a perfect thumbnail would be like, the video, I don't know what it's going to be called, like world's, prototype of the world's oldest, ray tracer or something like that. But just having ray tracing in the title and then having an image of this device, I think I'd definitely click on that. I'd be like, oh, that's interesting. Like I want to hear what this is, So anyway, I've got a bunch of like things like that I want to talk about. But I think what I've realized recently is I just have to put content out. Like that's where I'm at. I just need to make stuff, put it out there. And if I'm sufficiently interested in it, I think people will be sufficiently interested in it. And I think that's just what I have to go with, So again, the thing, I'm actually really excited for this one. I'm going to buy the heartbeat monitor soon. This one I'm pretty excited for, again, because it has some new research associated with it. This one I'm pretty excited for as well, because it's a combination of domain coloring, color quantization, a weird pixelization method and stuff like that. Oh, another one. I'm sorry, I'm rambling too much. But another one I wanted to do is a tlog. Hear me out. It's a terminal log. And the idea with a terminal log is it's just a vlog, like regular vlog that you'd expect. It's just entirely done in the terminal. So like you can just open up your Xterm terminal and you can just watch the video there, as well as on YouTube if you want. But you could also just like pull it up on your terminal. I think that'd be really cool. This stream will hopefully be on YouTube later. Yeah, I should be uploading it there as well. I need to remember to click the button. It might be 24 hours delayed. I might wait a day before putting it over to YouTube, but it will be there. But also Quiltify, the stuff we're doing for coding a quilt, is actually incredibly useful for the tlog, because the idea would be that we just take an image and we or take a video and we just like turn it into these ASCII pixels, you know? Even if the vids are only interesting to 1% of people, that's still a lot of people. Just needs the audience to match the content. Looking forward to it. Have a great stream. Yeah, Sierpinski. I can never pronounce the name, but thanks so much for coming in, and have a wonderful evening or whatever time it happens to be your time. Anyway, that was a long ramble session. I do apologize for that, but you know the stream. I tend to ramble. Let's move into fractal compression, and let's see what I want to do on top of that. But yeah, I've got a bunch of these like cool ideas that are just new things that people haven't seen before, and I'm just excited to try them out, you know. And that's kind of where I'm at now. Like, don't get me wrong, we're still doing algorithms. All of the stuff we're talking about are still like deeply entrenched into algorithms and stuff. But I kind of feel maybe we don't do videos so much on here's an algorithm that you haven't seen before. Maybe we do videos on here's something really cool you've never seen before. By the way, all of the algorithms you're looking for are available on the algorithm archive if you want more information, you know? Okay, so finally, let's hop into fractal compression. I've been talking too much and getting nowhere. So let me get some water and let's go. Fractal compression is a lossy compression method for digital images based on fractals. The method is best suited for textures and natural images, relying on the fact that parts of an image often resemble other parts of the same image. Fractal algorithms convert these parts into mathematical data called fractal codes, which are used to recreate the encoded image. I feel like this is now way different than I thought it was. Askinema. What is that? Oh, you sent me a link as well, and I just... let me grab this link. 1 second. Paste it here. Yeah, something like this I think is what we want. Yeah. I think we're gonna want something like this in the end. I'm not really sure how we're gonna do it. But also like, okay, hear me out. One final pitch for you guys. A long time ago, I came up with this project called Spectrum, which was going to be my first attempt at a game, and I was going to make a terminal game. The idea was that you're this specter that goes back and forth between spectral space and real space, and it's basically a terminal game is the idea. But I wanted it to be like story driven and like, you know, emotional and all of this kind of stuff. Like I really wanted it to like sell a story to people. And I wanted to use it as a way to basically like do a bunch of algorithms that are related to game development, but not necessarily like in a way that is easily understandable, right? You know, because I figure pixels in a terminal game are way easier to understand than like, you know, a 3D mesh or something like that. And in addition, like things like music generation, like algorithmic composition and stuff like that would work better in a game like this than would work in a game where like you really care a lot about production quality and stuff like that. So I've been thinking about revitalizing this concept, you know, like, you know, a story-driven terminal game. But inside of that, we also like, you know, talk about algorithmic composition. We talk about like, you know, how we used flood fill for this thing. We talk about, you know, all of this type of stuff. And I think all of that is really good stuff that would fit perfectly well into the problem of the week category, right? Like it's just like this week, all we're doing is using flood fill to do this one animation for our terminal game. And that's it. And that's our problem this week. That's what we're solving, you know? I think, I don't know, it's kind of the same level, of the same feel. But I feel that because it's related to game development, it doesn't have the same broad appeal as the other stuff, you know? But you know me, I love terminals, so anything I can do to like put a terminal into a video, I will do. Okay, so let's go back to fractal compression and let's just get through this article, I think, by the end of the hour. And then we'll work on the next PDF after that. Okay, iterated function systems. We've already talked about iterated function systems. I'm going to read this, but the assumption is that we already have an understanding of this. So fractal image representations may be described mathematically as an iterated function system. Right. We begin with the representation of a binary image, where the image may be thought of as a subset of R squared. If an iterated function system is a set of contraction mappings, you gotta love Wikipedia. F of I is R squared onto R squared. According to these mappings, the iterated function system of a two-dimensional set S as a fixed point of the Hutchinson operator H, right? So the Hutchinson operator is a set of all possible functions in the function system, right? So it's just a combination of all functions in the iterated function system is the Hutchinson operator. That is, H is an operator mapping sets to sets, and S is the unique set satisfying H of S is equal to S, right? The idea is to construct the iterated function system such that this set S is the input binary image. Okay, I got to think about that one really quick. The set S can be recovered from the iterated function system by fixed point iteration for any non-empty compact initial set A0, A0. The iteration A of k plus 1 is equal to H of A of k converges to S. Okay, 1 second, we got to think about this one. Let me finish reading this paragraph, and then I'm going to come back to try to parse it. The set S is self-similar because H of S is equal to S implies that S is a union of mapped copies of itself. S is equal to F of 1 of S with F of 2 of S with F of N of S. So we see the iterated function system is a fractal representation of S. Okay. I am also completely lost. Like, this is this is a bit tough. So, okay. It is saying that we have a binary image, and the binary image, I think, is just black and white. That's all it is. It's literally just a black and white image, right? So this is a binary image. Totally fine. Great. That's big. Let me make that smaller. 1 second. Okay. So that means we start with some sort of black and white image, and we say that that black and white image is our initial set S. Now, my issue with that is I don't understand how... I don't understand how the set S is related to the function F. Okay, that's where I'm stuck at. So F is any operation from R squared onto R squared. Yeah, I'm trying to make it big and small. I'm trying. Okay. So we have S is a unique set satisfying H of S. So if you apply H onto S, it's the... So, okay. What we're looking for here is a set of operations. So, for example, the set of operations for the Sierpinski Triangle was just a set of triangles that bring you, or a set of operations that bring you half towards A, half towards B, and half towards C. And here what we're saying is we're looking for a unique set satisfying H of S is equal to S. So this means that if you apply... basically what you're doing is you're just trying to find... you're trying to find a set of operations that will take in the binary set. Here's what you're doing. This is what you're doing. Let me try to explain this. So journal, new page before. You have an image, right? And the idea is you take this image and you turn it into a set of points, right? We'll say set of pixels, right? Now what you're looking for is a set of functions that will provide you back this image, right? So if what you want is a set of pixels that basically you're looking for a set of functions that will take any set of pixels and return back the image, right? Because the way the iterated function system works, again, is that the end of the iteration, as you iterate through all of the different function systems, you eventually land on the attractor. In the case of the Sierpinski Triangle, the attractor is the triangle of triangles, right? So in this case, you want the attractor to be the image. And the idea is you basically want to be able to create this set of pixels, a set of functions that will turn the attractor into the image. That's my understanding. What is a contraction mapping? Good question. I don't know. Contraction mappings here. Contraction mappings. In mathematics, a contraction mapping or contractor on a metric space M of D is a function f from M to itself. Okay, with the property that there's some non-negative real number 0, k, 1, such that for all of x and y in M, d of f of x, f of y is less than k, d, x, y. So I think it's just maps point to a region space, the subregion of that region. Right, so like, how's the best way to describe that? You take a set of points. Right, so here's my understanding. We take a box. A contraction map would mean that after after the contraction here, the box is like, for example, rotated or something, but it's still within the size of the other. So the box is a region, and then you do a contraction mapping and it just contracts it. It does something to it. Like, you might shrink it, it might rotate it or something, but it will be smaller and within the subset of the other region. That's my understanding right now. I might be wrong. So, right. So let's keep going. This is a Wikipedia article, and it definitely does not describe everything as thoroughly as I would like. But that's okay. That's okay. Let me actually go to Google Scholar real quick. Google Scholar, and let me take a look at. I find that sometimes just reading the source here. Let's go to Fractal Compression. Fractal image compression. What do we have here? Maybe we just read the source PDF for this. I often find that just like reading the paper is sometimes better than, you know, anything else we could do. It's a full book. Let's see what this is. All right, let's just pull it up. See what we got here. ADA, whatever. It's fine. How do I get rid of that without whatever? Screw it. Okay. So I'm gonna move that over to our directory over here. So we're gonna move. I think it was downloads AD. What was it called? Oh no. ADA. There we go. Right here. And I'm just gonna open up in Zernal, and we're just gonna see what it says. ADA. Perfect. Make it a bit bigger. This is an old paper. All right, let's see what happens. Move this over here so we can read it. And let's make it a bit bigger. The 2 in the corner. All right, what do we have here? I'm gonna use the highlighter, and we're gonna, yeah, pink is fine. Perfect. Oh, I remember there's something weird about the highlighter here. Yeah, it's definitely something weird. Okay. Sometimes the old paper is the best. No doubt. Ooh. Okay. It doesn't seem how it's from July 4th, 1991. In the 90s, there was a lot of research into fractal compression. Definitely, yeah. I think this is something that people just lost interest in because people lost interest in fractals. Who knows? Maybe what we're doing today will get like more people into fractal compression. Then all of a sudden, we can have like a fractal compression. I don't know. It doesn't matter. Okay. Some of the work. During the period of May to July 1991, we concentrated our development efforts into 3 areas: a survey of applications, algorithm development, and theory. We are also continuing to evaluate hardware needs. What are we reading? Applications. We've begun to select specific applications for our compression algorithms. Our selection process is based on information gained through technical discussions with commercial groups selling image compression hardware and software, literature reviews, and performance figures of commercially available software. Cool. The industry standard JPEG for image compression is based on the discrete cosine transform. We have chosen to evaluate the suitability of fractal method in comparison with this transform. Several key differences are apparent. Cool. Yeah, okay. How does it compare to JPEG? It doesn't look like they have any benchmarks, though. Dear Dr. Okay, enclosed is our first quarterly progress report. Yeah, first quarterly. Maybe we should... Let's see if there's a better... Using fractal compression scheme to embed digital signature into an image. Fractal image compression. Maybe this one's better. Okay. Barnsley.pdf. This one looks cleaner. Why not? Yeah, this one looks cleaner, doesn't it? I mean, it's just a big image of a blimp, or what are they called? A hot air balloon. Yeah, okay, let's read this one. I like this one a bit better. Well, okay. What do you guys want the old one from 1991, or do you want the new one from 1995? I'm sure. Where is this one from? It's from 1996. Like, do you want something that's 20 years old, or do you want 30 years old? Do you want something that's 25 years old? We'll do the 25-year-old one. All right, what did we save this to? Barnsley dot something? Whatever. I'm flipping through so many desktops, I don't know what's going on anymore. Okay, let's discard that. Let's go over here and let's just move downloads Barnsley.pdf here, and let's do Zernal. pp barnsley.pdf. All right, zoom in a bit, move this over here, and let's just kind of go through it, see what we got. Also, I'm just going to say something. I am super excited to do something that, you know, I realize this is not like groundbreakingly new research. It's not something that like, I've been needing something that scratches that itch of like just new stuff that I'm learning for a long time. For years, I've been needing something that's just like, hey, this is something new that you haven't learned before, just learn it. And I'm super excited that we're just like learning stuff, you know? Like, I completely understand it's not everyone's cup of tea. I understand some people are probably turned off from like weird Hutchinson Operator like notation up here. Totally fine. I'm really enjoying it though. So I'm hoping that some people in stream are also enjoying it, and that this is, I don't know, useful for you guys, you know? Okay. What do we have here? How many pages is this? How long will this take to get through? I think we can probably get through this in, by the end of the hour, and we'll see what we need to go from there. Okay. Top-selling multimedia encyclopedia Encarta, published by Microsoft Corporation, includes 1 CD-ROM. Oh no. 7,000 color photographs, which may be viewed interactively on a computer screen. Includes on 1 CD-ROM. Hear me out here. Includes on 1 CD-ROM 7,000 color photographs, which may be viewed interactively on a computer screen. Oh no. You know this is an old paper. This is from 1996. Oh no. Like, you know, image compression has to be great when everyone like stopped doing it for other compression methods. Like, you know, this is the best compression method we can go with. How old is this? I'm like the kid that likes trains, turtles, but for me it's fractals. Fair enough. Fractals now in Technicolor. They use everything Carta. I don't know. The images are diverse. They are of buildings, musical instruments, people's faces, baseball bats, ferns, etc. What most users do not know is that all of these photographs are based on fractals and that they represent a seemingly magical practical success of mathematics. Honestly, in terms of science communication, that's not a bad opening paragraph. Like that, that's a pretty good intro. Research on fractal image compression evolved from the mathematical ferment on chaos and fractals in the years of 1978 to 1985. Oh boy. And in particular, on the resurgence of interest in Julia, the programming language, sets, and dynamical systems. Okay. If any of you guys have read like the old papers, like, you know this is true. Like, everyone was super into chaos for some reason in these dates. I don't know why. Just people were super into it. For better or for worse, that was the clickbait back then. Microsoft's open image compression format is pretty good, but don't remember the name, but it's best candidate to replace JPEG. Yeah, so we are going to find a better candidate to replace JPEG. That's our goal. We go back to 1970s and we find some ancient tomes of knowledge that they had back then that now are just going to flat out defeat any modern, you know, compression method. That's what we're going for here. So here, I briefly describe some of the underlying ideas. Following Hutchinson 7, see also 5, consider first a finite set of contraction mappings, Wi, each with a contractivity factor S less than 1. Taking a compact metric space X into itself, I is equal to 1 to n, such a setup is called an iterated function system. Are iterated function systems always contractive? I didn't know that. Use this iterative function system to construct a mapping W from space H of the non-empty compact subsets of X into itself by defining in the self-explanatory notation this guy. Sure, let's go with that. Oh, it's a nice box. When W is a contraction mapping with contractivity factor S less than 1 with respect to the Hausdorff metric H on big H, defined as the following. See, like, I just told them. I just said, oh wow, what a good intro paragraph. That's what I just said, and then they completely lost me. Like, I have no idea what they're talking about now. You know, like, get some more water really quick. What are you doing next? 46 decline push-ups. So for anybody interested in research, this is what research is like. You get a good intro and then a bad second paragraph. Okay, when W is a contraction mapping, right? Okay, so just for the record, for those who may not be following, this right here is, I'm going to put it in blue inside of the pink. That right there is the same as the Hutchinson operator that we had before. It is a set of functions applied to B in order to basically iterate through a function system, and B is within all of H. Now, what is H? H is the space. So it's like a 2 or 3 dimensional space. So H is essentially like R squared or whatever, or R cubed or whatever, which is fine. You know, we're getting there, you know. JPEG XR is the name of the format. Fair enough, yeah. I mean, yeah. Okay. So then we have when W is a contraction mapping with contractivity factor of S less than 1 with respect to the Hausdorff metric H on H. Now the question is, what does the Hausdorff metric have to do with this? In fact, what is the Hausdorff metric? Hausdorff metric. What am I dumb here? Does everyone know this, or am I the one that's lost? 9 times out of 10, I'm probably the one that's lost. Let me re-highlight that over here. Okay. So H of AB, they see the push-up folder. So H of AB, which is a Hausdorff metric, is equal to the max of D of AB and D of BA. Is that not just like what is that called? What is X? Hermitian? It's a fractal dimension, I think. So H of AB. What is going on here? So H of AB is equal to the max of DA and DB. Okay. So what is DAB? Is the max of D of XB, and DXB is the minimum of D of XY of Y within B. Okay, so what is D then? D is, where is D? I can't find D anywhere. Oh, D must be some arbitrary function then, right? So if you have, an arbitrary function D of XY, and the minimum of that is going to be D of XB. Okay. And B is what? B is B is a location in space. Gosh darn it. I need to find a better way to do this. Okay, so B is a location. Let's just write this down. All right. Let's just kind of go through this. So this right here is the definition of the Hausdorff metric. So H here is the Hausdorff metric on H. So let's just kind of write this out, see what we got here. So we have B, we have A, and we have D. Okay, so what are these guys? So B is going to be your point in space. Totally fine. A, what is A? Is A just another arbitrary point in space, or am I missing something? Exactly one non-empty compact subset of A. Okay, I'm going to guess it's another point in space, but I'm not sure about that one. And then we're going to say D is going to be this function here. And it is a function that outputs 2 different things. If we have X and B and A and B, I don't fully understand why. And also, what's the difference between X and H? Okay, this is one of those times when I'm just going to do a tactical retreat from this point, and I'm going to assume that at some point we will understand this math, but that point might not be now, and we might just continue. We might just continue a bit. No, it looks like it just gets worse. I mean, these giant pictures of hot air balloons are really misleading, you know? You kind of feel like, I felt like, you know, with the giant pictures of hot air balloons, this would be pretty good. The first paragraph was like super like friendly to new people, and then it just gets crazy. So, moreover, H endowed with H, moreover, big H endowed with little h is complete. In this set W, in this setting, W admits a unique fixed point. there is exactly one non-empty compact subset of A of X such that A is equal to W of A. A is called the attractor of the A is the attractor. Okay, good. So A is the set of points. Okay, points on the attractor. That's what that is. There we go. Points on attractor. Perfect. So the attractor is the Sierpinski triangle, and B is any arbitrary point in space. So what is D then? What are these guys doing? So what these guys are doing is they are taking in any point on the attractor and any point in space, and they're saying, okay, so do we even care about the Hausdorff metric? So with contractivity factor of S less than 1 with respect to the Hausdorff metric, how is S related to the Hausdorff metric? H. Okay, maybe because this is all the definition of H, which is the Hausdorff metric, maybe we can leave that and we can come back to it. I don't fully understand how this is related right now, but we'll probably understand later if we just keep going. So now following 3, assuming that big X is a suitably large subset of R squared, which is all real space, and that each of these transformations, Wi, is an affine map expressed by 6 parameters. Perfect. Then the corresponding attractor is uniquely specified by the sets of numbers A, B, C, D, E, F, which describes the maps. Given a black and white image, which we model as a compact non-empty subset of T on R squared, that's totally fine. Like, each of these points in space is somehow mapped onto R squared. And I think that's fine, right? Because it is a 2D image, and essentially what we're doing is, I think the R squared here is, what is R squared? I don't think R squared is this box. Like naively, I would say that R squared is this box, but I don't think that's true. Where's my little rectangle? There we go. I naively thought that R squared would be the box in which all points are located, but actually I don't think that's true, because that's not a real space point. Like, real space is usually like X and Y put together, right? So if real space is X and Y put together, then you probably want some sort of floating point precision. This isn't floating point precision. These are integers in an array. So is R squared the amount of black and the amount of white? That doesn't make sense. That's just a 1D. That's R1 for each point. So is R squared, like, for example, when we did color quantization, for example, we specifically said that that is a 3-dimensional space. You have R space, G space, and RGB space, right? So that's R3. So Hausdorff's metric seems to be take every point in one set, find the distance to the closest point in the other set, do it again on the other set, and the largest of all these distances is the Hausdorff metric. So take every point in one set, which is going to be the attractor, like the Sierpinski triangle. Find the distance to the closest point in the other set, which is all space. So the closest point to the attractor. And you do that again on the other set. And the largest of all of these metrics is, okay, so we're asking if we have a random distribution of points, which is B. The question is contractivity factor. Right. So the question is basically what is the distance between the random distribution and the attractor, essentially, is what we're looking for. And so, like, for example, if we have a square here, I'm just spitballing, I think this is correct, but I might be wrong. So if we have a square here, and we have a triangle within said square, and it's a Sierpinski triangle, so we're just going to draw a triforce, and a triforce inside the triforce. Then the Hausdorff metric here, assuming we have a point down here, would basically be is it the maximum distance? Oh, no, it would be from here to here. So that's the Hausdorff distance from these 2 points there. And I think that's fine. It's the largest, smallest distance between the points. Yeah, so that's what it is. It's going to be these 2 distances here. And that is fine. And what we want that to be is less than 1, so we can make sure that we are contracting. I think that's what we want. We want to make sure that that is less than 1 so that we are contracting. And I think that's fine. I think. Okay. So now my next question, hey, that you're fan, how are you? Is what is r squared? in this metric, like again, like I said before, when we've done color quantization or something like that before, the color quantization was specifically taking an image of colors and turning it into r cubed, which is RGB space. So the question is r squared just black white space? Do you need a separate metric for black and white? I don't think so. So now following 3, suppose that x is a suitably large subset of r squared, and that each of the transformations wi is an affine map expressed by 6 parameters. No, I think I know what we're doing. Okay, in the same way that an iterated function system, or in the same way that the fractal flame method, will generate images that look like, let me just pull up an image for you. Let me do here, CD projects, simuleos, sorry, I think I need Flamify. And then Mirage, save, 1. Okay, I think I understand what's happening here. So when we generated this image, there's 2 things that are happening here. One, we have the unique placement of an individual particle in space. So like if we go up here into the corner, you'll see that essentially we have all these particles in space, right? And then we have like this kind of colored pink region, right? And so the idea is that r squared is the location of that point in space. But you create a density map. So the very black regions are where you have a bunch of particles, and the very white regions are where you have few particles, or vice versa. So it is r squared. Sorry, it is r squared because we're taking a bunch of points, and the density of those points are what determines like how the image is generated in the end. We basically bin it together. So I think this is fine. I get it. I'm a bit slow, but I'm slowly getting it. Okay, right. So I think that's fine. I think we can adequately represent r squared. Totally cool. We can choose the coefficients of an iterated function system of affine maps so that its attractor is an approximation to t. Okay, so t, in this case, is going to be the initial image. And what we want is a coefficients in an iterated function system of affine maps so that its attractor is an approximation to t. Right, this is almost identical to the concept that we had before of turning any image into a set of fractals. In fact, it's the same thing. It's just that what we were doing before is we were saying that the set of fractals is created from a set of fractal flames, right? Here they're saying that each fractal flame is itself generated by the method. Let's keep going because I think we're slowly getting there, right? The idea is that we're basically creating some sort of operation that allows us to take any points and basically, yeah, the attractor should be an approximation to the image. So that, okay, let me try that again so it's not a strike through. Let's do that with a highlighter. The attractor is an approximation to t. That's what we're looking for here. So the idea is we want a set of points whose attractor is essentially the image, and the attractor again is basically the attractor is basically the like the Sierpinski triangle in the case of that affine iterated function system. So to achieve this, we seek coefficients for the mappings wi so that h of t of wi is suitably small. Right, for the contractivity of W implies the estimate here. Yeah, okay, this is exactly what we were saying before, right? We want it to be suitably small so that we can do some sort of contractivity mapping. Now, I still don't fully understand where S is coming into play here, but you know what? We're getting there. Like, slowly but surely, we're getting through this paper, and I'm happy with that. So, yeah, let me get a little bit more water. What is this? What is it about? So the paper is about fractal compression. It's like basically it is a competitor to JPEG in a way, in which they are taking an image and they are turning it into what is known as a Hutchinson operator. They're taking it into a set of functions that can they're turning it into a set of functions. Thanks for the push up, by the way. That can recreate the image, right? So in the case of most iterated function systems, you will generate some sort of thing known as an attractor. So you generate a Sierpinski triangle, you generate something that is an attractor. And so here, that attractor is an image, and that's what it is. I'm actually here now. I'm doing fine. Hope you're doing well. Yeah, how are you? I'm glad to hear you're doing fine. I hope that, I haven't seen, like, because I've been off and on for streaming for the past few months, I haven't really been doing a very good job of keeping up with the community. which is again another reason why I'm so excited for this, like, you know, like, what's it called? Problem of the week type of thing. Like, I'm really excited for that. I think it's going to be really cool. I think if we, like, again, I think Fulcher's right. There's no way, unless I get really, really good in the next, like, year, that we're going to be able to do problem of the day. Like, I really wanted to do something that, like, kind of pushes at that boundary of research, like, every day, but that's probably impossible. Do I look like I know what a JPEG is? Yes? Summit3301, thank you so much for following, really appreciate it. Okay. Let's get through another paragraph or two, then we'll do all the push-ups. A lot of push-ups. We have 46 decline push-ups. That's fine. Hank Hill emote would be a great to have. Oh, fair enough. I've never seen that show. Okay, so let's get through this paragraph. Let's do the push-ups, and then we'll move on to the next set. I'm gonna modify the exercises so we don't have like 55 decline push-ups to do. 1 second. Let me do that right now. So I'm just gonna go into VI exercises. Where are we? Exercises, arms. Also, how did we get another arm exercise so soon? I don't exactly know how that happened. So you have decline push-ups, 1 to 100, diamond push-ups. Let's drop this down to be maybe 70 or something. And let's say instead of doing 46 decline, let's do 35 decline push-ups. And that should be fine. Right, and quit there. Okay. How 20 to 150 dips? I said you could do. Let me drop this down to 100. And we'll see how that goes. Okay. So I'm going to actually just, you know, drop down the number of decline push-ups. I'm just going to do 35 instead of 46 this hour, but that's okay. I saw the random exercise video you made. Cool stuff. Yeah, the thing is that video did like super badly. Like it was, I hit the microphone. Sorry about that. It performed worse than like any video I've put on YouTube for the past 4 years. But my hope is that from here on, it can't get worse than that video. Like all the videos I put out from now on should hopefully get more views than that one. But I thought it was a really cool, I thought I tried my best on that video. Like, you could argue that maybe it wasn't great, but I'm going to argue it's probably the highest quality video I have on my channel. Like, I tried my absolute hardest on that video, but that's okay. Okay, let's get through this paragraph, and then we'll go ahead and do the push-ups, and then we'll keep continuing through this article. Again, my hope is to kind of understand fractal compression by the end of today. It's a great idea to stream and read research paper or study a topic. I usually find myself studying more effectively when I speak and read. I actually find the opposite, but at the same time, I feel like it is good to do some of this on stream. I wasn't planning to do a lot of research, like just reading of articles on stream. I was planning to do the actual, like, you know, coding and thinking through bit on stream. But you know, it's all part of the process, and I'm happy to do it. I was just hoping to do a lot of this off the stream as well, because I do know that like reading research articles on stream is something that, yeah, probably very few people are actually interested in. So, okay, what do we have here? So this tells us that if t is close to w of t, then the attractor cannot be far away either. For example, the well-known Barnsley fern represents the attractor of an iterated function system of 4 affine maps, which were chosen so that a fern image t was mapped approximately to itself under the corresponding w. Okay, correct. Yeah, I see what they're saying. Yep. So in the end, the Barnsley fern is a typical attractor image. Oh, Sumit, thank you so much for the subscription. Let me go ahead and put a Simo account in chat. I really appreciate that. Thank you so much for the support. Copperboats did decrease the difficulty of the next set. Let's go ahead and do that. Set decrease difficulty. How many is that? If that, let's do reps again. So that's a total of 37. Yeah, let's do 37. That seems good. Again, I dropped it down for next time we get decline push-ups, but it should be good. But yeah, thank you so much for the support. Really appreciate it. YouTube really rewards consistent uploading. It's like the duck debugging method. Speaking out your thoughts helps them being organized, but also specifically speaking out your thoughts on stream gets more people interested in the topic, right? So, like, for example, I was not intending, when we were talking about fractals and the generation of the iterative function system and all that kind of stuff, I was not intending to touch the spanning tree idea. I was just mentioning it, and then we were going to move from there. But actually, this idea of maybe iterating through trit strings could actually be a better way to do it in parallel than going through the chaos game. Maybe. I don't know. It's an interesting question. I have no idea. We're going to have to test it. So, like, we're going to write down what we need to do. But right now, we're kind of learning about image compression and how it's related to everything else. Hey, Morton, how are you? Okay, so we basically said here that the Barnsley fern is the image T that was mapped approximately to itself under the corresponding W. Okay, so C2 for more details. In this manner, a fern subset of R squared may be encoded using 24 bytes, okay, of data, namely 4 maps, each requiring 6 parameters, each represented by an integer and the interval 0 to 255. That's what we need. So this tells me that there is a small memory footprint. What they're saying is instead of keeping track of the image, or instead of keeping track of like any points in space, what we're keeping track of is instead the transformations to allow any arbitrary point to turn into that attractor, right? So we're basically recreating an image via a chaos game, which is really cool. I love that idea. And I think the rest of this paper will outline how that's done. I think this is a good place to go ahead and hop into the push-ups. Again, I've got, how many push-ups do I have to do? Oh, I'm sorry, I have the wrong screen up. It's 37 decline push-ups, and then where's our normal push-up counter? It's just flashing 37 decline push-ups? Let me do this, and then maybe that will regenerate the image. I just realized it's just flashing 37 decline push-ups. It was supposed to say, yeah, push-ups 4, there we go, and then 37 decline push-ups. That's a lot of push-ups, guys, but we'll go ahead and hop into that, and then after that, we're going to continue with the fractal image compression, and yeah, that's what we're going to do. So for those of you guys who might just be hopping into stream, you haven't seen the stream before, what we do is a 5-minute exercise at the top of every hour, followed by an hour of just trying to figure something out and doing some sort of defined project. Last hour, what we did is we hopped into the fractal compression concept, and we picked out a paper, we started reading it. So next hour, the goal is to finish up reading the paper, try to understand it a bit better at a more intuitive level. And then after that, we're going to talk about how we're going to maybe use this concept to basically create that fractal filter idea, the idea of turning any image into a fractal. And basically, we want to suss out all of the details by the end of the hour. That's what we're trying to do. Morton, thank you so much for the follow. You can always think of less pushing yourself up and more asserting your dominance by pushing the ground down. Right. So for the 5-minute exercise that we have this hour, we have 4 push-ups to do, followed by 35 decline push-ups. I will basically be sitting, like putting my legs on my bed to do the decline push-ups. You guys don't have to join along for the push-ups. I would encourage you guys just to get out of your chair, walk around, get that blood flowing, just something to take your mind off of whatever you were focusing on before. And I now have 5 push-ups to do. Thank you. And that's the plan. So I'm going to go ahead and change microphone position, and I will be back in just a second. I don't think we have jumping jacks yet. They might be next, though. We'll see. So guys, give me just a minute. I will change the microphone position, change the music as well, and we should be good to go. Cool. 1 second, guys. Okay, let me move the, oh, you guys probably can't hear me, the microphone's down there. One second. Okay, let me put the chat up down here and then we'll go ahead and get started. Again, guys, you guys don't have to join along. The point is just to do a little bit of exercise, get that blood flowing just a little bit more than you normally would, and maybe break up the monotony of the day of just, sitting in your chair and watching people stream and stuff like that. The idea is kind of pog. I don't know, 35 decline push-ups might be a bit much, but we're just going to see what we can do. I think it'll be fine. Unfortunately, push-ups requires acceleration, and so you can tell that you're moving. The earth is not. Fair enough. Okay, so I'll do the 5 normal push-ups, then the 35 decline push-ups, and we'll go from there. All right, 1, 2, 3, 4, 5. I hit my nose really hard against the ground on that last push-up, and it was, that was like, I mean, if it was any more forceful and I wasn't against this mat, that would have hurt a lot. Anyway, let me move the camera. So, well, actually, the camera might be fine. If I just do this, it's still fine. You guys can still see me okay. Okay, so 35 decline push-ups. What does that mean? That means I'm going to do a set of 15, I'm going to do a set of 15, 2 sets of 10. That's what I'm going to do. It's going to suck. I'm really sorry about that. We're still kind of working out the kinks in the Swole Leo's workout software, so it's sometimes a bit higher than it needs to be. And this is one of those cases where I think probably it's a bit too high for what we want it to be. Oh, 37 decline push-ups. Oh, we'll do 15, 10, 12. That's what we'll do. All right, so I'm going to go ahead and go. And feel free to join if you guys want to. Again, if you don't want to, that's totally okay. We'll get back to programming in about 5 minutes. Just maybe take a few minutes to rest, stand up, walk around, chill for a bit, and we'll be back to programming in just a second. I think this will work just fine. Okay, let's see how this goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Ugh. Okay, so now we have, let's see, another set of 10, another set of 12. I'm gonna give myself just a little bit of rest so I don't like fail miserably on stream. Oh gosh. I hate push-ups too. Like why are we doing a push-up counter? Like of all counters, like I could have done any other exercise. Jumping jacks counter would have been better. Push-ups suck. I have like no chest muscles, you know? I mean I do, but like they're useless muscle groups. Pecs are so useless. No one cares about this region unless, I mean, not if, you know what I mean. Okay, set of 10. All right. Up. 1, ooh, that's weird. 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. All right, the last one's a set of 12. I'm gonna give myself just maybe 30 seconds rest. Hope you guys are all having a wonderful day. Again, we're not going to be doing another exercise for another 55 minutes or so, but it's good just to get up and do something a bit different every now and again. Whew. Oh, these are, I love push-ups. In that I really hate them a lot. Also, I'm going to be taking a quick minute break just to get a little bit more water. I'm about halfway out, and I'm pretty sure after I drink water from this little, 10 or 5-minute workout, I'm gonna need to get some more. So I'll take just a 2-minute break right after this, and we'll get back to the fractal compression. Okay, last set of 10, actually set of 12 to get up to 37. Okay, set of 12. Let's go. Wait 1 second. I like this idea. Just wondering, you try to implement stuff from different research papers. Is it yours? Yeah, so this one right now is not my research paper, but we are slowly but surely working up to where we're hopefully going to publish a research paper, or maybe at least get to the point where we could publish a paper. Maybe the findings are interesting enough that we can. The point right now is just to kind of touch the area, like move in that direction. Thanks for chatting, by the way. That way I could take a little bit more rest on the push-ups. Okay, set of 12. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so that was a set of 37 decline push-ups. I'll be right back, guys. I'm gonna change the microphone position, get some water. I'll be back in just a minute or two. Sorry about that. Whew. Okay. Is that right? Oh, okay, again, guys, I'll be right back. So give me about a minute, and then we'll get back to the fractal compression. Okay guys, I'm back. Give me just a second to set everything back up. I'm going to turn this music off, turn that music on, turn this light off. And yeah, we should be good to go. 1 second. Forgot about the whole chair situation. What do we have here? It feels good to get the blood pumping. That's good. Love your stream. I'll try to follow along for the next time. Gotta go. Yeah, see you, man. Thank you so much for coming in. Have a wonderful evening or whatever time happens to be your time. We have an additional push-up by Morton. I don't know if I added that last time or not, but I'll just go ahead and add it this time, and that should be fine. So we're back to 1 push-up for next hour, and we need to create the next set as well. So let's see what it's going to be. Over here, we're going to, what do we have? Cycle set. The next one's going to be mountain climbers. Oh, probably 55 as well. Reps. Yeah, 100. 110. We have 110 mountain climbers. Okay, that's fine. Sounds good to me. 110 mountain climbers. That'll be fine, right? Probably. Mountain climbers are deceptively difficult, so we'll see what this actually does in the end. Okay, so back to the fractal compression method, and we're just going to see where this goes, you know? Also, guys, if you have any questions, comments, concerns, ideas, anything like that, as we're going through the topic, feel free to let me know. For those of you guys who might just be jumping in, and you didn't see us for the last hour, essentially what we're doing here is we are trying to create essentially a fractal image filter, turning any image into a set of fractals. We want it to look cool, but also it's very close to this idea of fractal compression. So what we're doing is we're kind of going through and learning a bit about fractal compression to see if there's anything that we can learn from that before implementing our own fractal filter. That's kind of where we're at. So far, what we've learned is that, you know, essentially fractals, the way fractal compression works is you take in an image, and you're trying to create a set of functions which will basically allow you to take any points in space and recreate that image. That's kind of the idea. You want the image to be the attractor of your set of function systems, which is really cool. I really like the idea. I'm interested to see where it goes. So let's just keep reading. So how is a photograph, such as shown in Figure 2, computed? First, the theory of iterative function systems is extended to local functions, wi, such that w minus 1 of I is from d of I to r of I. Oh, okay, I don't really know. How do you compute the inverse of a function? It's probably fine. 1 over f. Maybe I'm dumb. I feel like I'm dumb. This is a mathematical function, right? Just gonna Google this really quick. I want the inverse of an arbitrary function. Is there a method to find an inverse of an arbitrary function? In general, no. Yeah, that's what I thought. Good. Okay, so I'm not an idiot. Right. Okay, this is okay. We'll figure it out. Also, let me go here. Do I need to change the camera location? Maybe a bit. Okay, there we go. And let me do this. Okay, right. Yeah, that's what I thought. I don't think they all have inverses. I think it depends on the function. Okay, so where the domains d of I and ranges r of I are subsets of x, for I is equal to 1 to 2 to n, associated with an iterative function system of such functions, we define this, which looks like it's just a Hutchinson operator, essentially, of all of the different operations. And under the appropriate side conditions for such operators, continue to be contractive. Oh, under appropriate side conditions, such as operators continuing to be contractive and to admit estimates of characters of equation 1. What is equation 1? They don't have numbers on their equations. Oh, here it is. Functionally have inverses if they're injective. Yeah, that sounds right. I'm not really sure. Okay. Also, I haven't taken calculus class in such a long time. Let's just go highlight this guy. Again, this looks like it's very similar to the Hutchinson operator. Such is the case in the following setup. A grayscale photograph image may be modeled as the graph g with an r cubed of a function f, which is a set onto r that represents the intensity or brightness of the image on its support. S is I don't know what that symbol means. It's not within. I read this as within, but that's actually not within. Is that without? What does that function mean? I think they need to be bijective. Okay, so then one seeks a local iterative function system of contractive affine maps on R cubed such that W location of G approximates G and such that the projections P of I of the domains D form a partition of S. Okay. In typical implementations, S is a rectangle and the PIs are square tiles. For each I, to find a suitable contractive mapping WI, one searches in a digital computer implementation for the best match among some set of affine transformations between W, there we go, that's what I wanted, between W, R, whatever G, and the portion of G that lies above P of I is measured, say, by the minimum root mean squared error. So this right here tells me that they are essentially doing almost exactly what we were going to do. So this square in here, basically, oh gee, I can't draw, just for Pete's sake. Let me try this again. This, oh, just I can't do it. I just can't. Okay, I'm just gonna shade it in. All right, this square in here, this area in here, all the way down here, basically says that. Is that going to color? Yeah, there we go. I suck at it, but that's okay. That's a subset. Oh, it's a subset. Okay, fair enough. So wait, what's the difference between... Okay, I'm going to ask a stupid question. What's the difference between this symbol and this symbol? Belong? No, it's fine. But anyway, what this is saying is essentially they created some sort of weird optimization. Optimization strategy, right? Based on the root mean squared error to the image, which is essentially the same thing that we were looking at before. So we wanted to find some sort of error associated with how close our fractals come to the image. The second is for sets, the first is for elements. With the bar below is subset. There's a lesser or equal to. Okay, right, so this one right here is for sets. Oh, no. This is for elements, and this is for sets. Great, okay. I didn't know the distinction. I appreciate that. The coefficients and other descriptors of the selected local iterative function systems are called fractal transformations of G. Its attractor provides a succinct approximation G tilde for G. Figures 2, 3, and 4 provide a simple illustration of fractal compression. Figure 2 shows the original digital image of a balloon, which is of dimensions 512 by 512 pixels, with 256 gray levels at each input. Figure 3 shows the same image after fractal compression, carried out as follows. Each channel P of I, from 1 to 16 through 8, whatever, that's just a number of, that's 512 by 512, consists of a square of dimensions 4 pixels by 4 pixels. Oh, maybe I'm wrong. Consists of a square. What is... That's 256 times 256, isn't it? 256 squared. No. What is 16383? How did they get 16383? Let's do 16, a square root of 16384. 128. Oh, it's 128 squared. Oh, because it's a set of bar... So it's a 512 by 512 image, but they parsed it in 4 by 4 squares. For some reason, I read that as 2 by 2 squared. Okay, that's totally fine. So, consists of the squares, dimensions of 4 pixels by 4 pixels, which, with the lower left corner of PI located at pixel J, that's fine, they're just locating the pixels. The contractive transformations WI are chosen to be affine of the form that, where A of I maps some square in the support of the image of dimensions 8 pixels by 8 pixels onto P of I. Each A of I is a similitude. This is a situation where I wish I understood English, but I don't. Actually, what is a similitude? It's one of those things I'd pretend to know if I was younger, but I don't. Counterpart double correspondence in kind of quality point of comparison. Fair enough. Simile, yeah, fair enough. With the bar below, 2 is an element of 2, 3. 2 is a subset of 2, 3. Right, I'm not 100% sure. Okay. So each A of I is similitude of contracted factor 0.5. The origin of coordinates is at the lower left corner of the image, and z is, they're just saying where everything is, that's fine. The allowed squares are all of the lower left corner at 2p, 2q. P of q is within 0 to 251, and the sides parallel to the axes, each of the 8 possible isometries but are being admitted. Blah, I just can't read this. The intensity coefficient C of I are restricted to lie on the set negative 256 to positive 255. The set of allowed affine transforms associated with each tile P of I can be represented using 226 bits of data, and that is because how is it only 26 bits of data again? I don't understand the 26 bits of data. We're gonna have to come back to that one. The set of allowed affine transforms associated with each tile. Okay, right. This article is literally just Fractal Image Compression by Barnsley. Ah, I didn't realize this is Barnsley himself. Nice, okay, I'll take that. The part of the original associated with a single tile requires 128 bits of data. Thus, the fractal transform file is approximately 1/5 the size of the original image. The decompressed image computed from the fractal file is shown in Figure 3. In Figure 4, we use the results of restricting the choices for P and Q. I think this is just talking about their methods. Yeah, the rest of this is just methods, I think. Yeah, that's it. So we can look at that, but I think really the better thing here is just to look at the images. So this is a 512 grayscale image with 256 gray levels for each pixel before fractal compression. So it's before fractal compression, and then this shows the results of applying fractal compression and decompression to the image displayed in Figure 2. I don't understand. Yeah, I don't understand. How did they? This shows the result of applying fractal compression and decompression to the image displayed in Figure 2 at a higher compression ratio than Figure 3. See the text? And this is fractal zoom on Figure 3 obtained by computing the attractor of the fractal transform at twice the resolution of the original. Okay, this paper is written by Fern. The expression with that union symbol was interesting. Okay, so this is not the original image then. No, that is the original image. I don't buy that. There's something wrong here. Yeah, there's something definitely wrong with this. There's no way it went from this to that. And the reason there's no way it goes from this to that is because if you look at the branch here, that is information that the fractals wouldn't know. And there's no way it goes from this to that, right? So my guess is that this is not 512 by 512. This is 128 by 128. That's my guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 4, 5, 6, 7, 8, 9. Yeah, this is 128 by 128. So this is after binning it into the 4x4 groups of pixels. Also the horizontal lines on the balloon. Yeah, there's no way. Yeah, it can't go from this to that. What this must be is... Yeah, this has to be after it's been binned into the 128 bins. So what they did... My question is then how and why they did the binning. Okay, just for people who are coming along, thanks for the push-up. No, that was a while ago. If someone wants to give me a push-up, they can. So this is my understanding of what they did. They took an image. It doesn't matter what the image is, but I'm just going to draw a box in here. And then they turned it into another image, which I guess I'm going to draw in blue, which, that was not what I meant to do. Chotomate. They took another image here, where the difference is this image over here was 512 by 512, 512 by 512, whereas this image over here is 128. Oh, come on. 128 by 128. Right. So my question is why they did this transition in the first place, and what they used the 128 by 128 image for. That's where I'm a bit confused. And they mention it here, but I couldn't quite follow their methods for this section. So it's in this section. We just have to kind of read it and figure that out. Cool. Let me get a little bit more water, and then we can keep working on it. By the way, guys, just to keep an eye on the time, I've been streaming for about 2 hours and 40 minutes now. So, it's been a significant amount of time. I know I keep asking for feedback and updates and stuff like that, and questions and all that kind of stuff. But if you guys do have questions, like if you guys want me to update, give, discussions and stuff like that, let me know. Again, we're just trying to just do research on stream. That's what we're doing here. And if this is interesting, I'm happy to hear that. If it's not, who knows? Maybe. Basically, what I'm going to try to do with this content, because I haven't mentioned this in a little bit, is I'm going to try to just like turn this into a problem of the week series, where our problem this week is why chaos games suck on GPUs. And that's the problem we're going to solve this week. We're just going to make a relatively effective chaos game implementation on GPUs. That's what we're going to do. So we're going to do a bunch of different implementations. We're just going to do whatever we can to solve this problem adequately in a week, and we're just going to put that out at the end of the week. The video is not going to be super highly edited. It's going to be really... It's just going to be like... I don't know how to put it. It's just going to be like a deep dive into the topic by talking about the research papers, talking about what everything is, like doing a review and stuff like that. The PDF viewer is Zernal PP. It's the same thing I do to write my notes on. But yeah, so if this sounds interesting, if you like this idea of just doing research every day and just trying to figure out how this all works together and maybe talking about more technical topics, let me know. I think I'm interested to hear opinions on that. I mean, most people here who are watching the stream will probably say yes. But it is a very big divergence, a very big change to what I normally put out, which are kind of higher level descriptions of topics. This will be more of a lower level, just like, almost technobabble-esque video where we're like, we're just talking about it. And I'm just going to explain why I'm interested in it and just be like, hey, this is what we have. If you're interested as well, just keep watching. Anyway, it's interesting to me. That's good. Thanks for that. Okay, so let's try to figure out what this 128 by 128 tile is actually tile set is actually doing. Because I'm a bit lost on where that's actually being used. So, okay, figures 2, 3, and 4 provide simple illustrations of fractal compression. Figure 2 shows the original digital image of a balloon, which is of dimensions 512 by 512 pixels with 256 gray levels at each pixel. That is not 512. I just counted. That's not 512 by 512. Like, that is definitely 128 by 128. With 256 gray level at each input. Figure 3... Am I missing a figure? I don't understand. What's the stomping sound? I didn't... Oh, you know what? I bet what's happening is I need to move this up here. Sorry. I didn't realize it was a stomping sound. My bad. It might have just been that my microphone cable was hitting something on the side of the table. We must have a paper command that gives you DOI of the paper. It's too much effort. I mean, maybe, but like... I could also just give you the link to the paper, if people are asking. It's this one. Oh no, it's not that one. It is this one. Copy link address, and then I don't think that's gonna work. Nope, that didn't work. How do I get the link address? That's it. There you go. Abort is escape. I did press escape. There we go. Google Scholar. Well, I mean, if yeah, it's free. But the papers might not be free on Google Scholar. It kind of depends. Simcoff, the author, red-handed. I don't know. I'm trying to figure this out. I mean, I'm sure the author is. I mean, it's Barnsley, right? Barnsley, Fern Barnsley. It's not like this guy's an idiot. They know what's going on. Cool. Okay. So what do we have here? Figure 3 shows the same image after fractal compression carried out as follows. Each tile of P of I, where I is equal to 0 to 1, consists of squares of the dimensions of 4 pixels by 4 pixels, the lower left corner, whatever. The contractive transformation Wi are chosen to be affine of the form of the following. Am I misunderstanding what's happening here? Maybe I am misunderstanding what's happening here. Okay, no, I think I understand now. This is the input. This is the input to the fractal compression. So what they did is they created a set of functions, and then they binned the image so that they could compress the image, right? That's what you're doing. You're compressing the image. So this is a compressed image. And then they're putting that through the set of functions to create this image in here. That's what they're doing. It's image compression, right? So you have to, this must be the compressed image. Yeah, that makes sense. I'm buying that. That's what it must be. If it's anything else, I'm an idiot, and I'm okay admitting that. So this is your compressed image. Oh, for Pete's sake. Whatever. Whatever. Pink. Compressed image. That's what it is. It has to be. 100%. Why is the input also an image? What do you mean? What they're doing is they're creating a set of functions. But I guess this method only produces noisy images. Details will be lost this way. Yeah, it's definitely a lossy technique. It is a lossy technique. So what they're doing is they're creating a set of functions that can transform one image into another image. And what they're trying to do is create a set of functions that will take an image and transform it into basically the very same image, right? And so then the idea is if you take another image that is kind of a messed up form of the original image, one that has most of the information but not all of the information, then you can put that through the same functions and you should be able to basically replicate the image that you were looking at to begin with. So that's kind of what they're doing here, because it will be lossy, no doubt it will be lossy, but it's not a bad representation. I mean, like JPEG compression is also lossy, right? The only non-lossy, like there are a few like non-lossy data compression formats, but this one is 100% a lossy image. What I would have loved to see would be the original image, and the differences between the compressed image, right? So I want to see the image after fractal compression reconstruction and the original image and see what the differences are. But maybe we do that. I mean, I think fractal compression would be something we do next week, but it's good to put it on the purview of things that we can talk about this week. This week, again, we're just going to try to create a quick iterated function system method. Why not train an AI that does the compression? In some sense, that's actually what the goal of our project is to do. Instead of doing an AI, we wanted to do a genetic algorithm. Right, so the project that we're working on right now is basically to take any image and turn it into a constituent set of functions. And the question is how to do that. And essentially, that is what fractal compression does. It takes any image and turns it into a set of functions, which are essentially fractal flames, with different operations, right? And so that's essentially what we're doing. Now, this tells me a few things, which is kind of maybe a bit disappointing, right? So let me just show some images on screen, right? So I'm gonna go over here and I'm just gonna take a look at this guy here. Okay, so before we were generating these images, which were fractal flame images, which look really cool, right? And so my hope was, and I know this is maybe a bit of a naive hope. My hope was that if we take an image and we turn it into a set of fractals, we would get like cool outputs like these, like things that look cool, but also like are reminiscent of the image that you put in. That was my hope. But it seems to me that if people are actually using iterated function systems, Hutchinson operators and the like, to do real image compression, it seems to me like we're actually just going to get the same image out that we got in unless we actually like do our best to lose as much information as possible. Like we're going to have to make what we're doing is we're creating a bad image compression method. That's what we're looking at. Some of the one-liner fractals that I've seen on ChaderToy are really cool. Oh yeah, no doubt. There's a lot of like really cool fractal generation methods and stuff like that. So, okay, just to write this down, because I'm a bit worried about it, journal new page before, and just to talk it out with you guys really quick. How do I put this? Right. So in the end, what I was hoping for, was a video that was called Becoming a Fractal. Right. And, like the joke is that, when I was younger, I wanted to be like an author, an inventor, a superhero, but never a fractal. Why not? Let's do it. Let me become a fractal. Wow. It's not really a joke. I don't know. I wasn't sure if I'd actually use that line, but becoming a fractal. Right. And so I wanted basically to snap my fingers and turn into a fractal and just like have that be like, just have Fractal James give the rest of the video. Like I had it all kind of planned out at how I wanted to do it. The problem is, you can compress the compressed image. Well, no, you can compress a non-compressed image. Wait. Oh, are you saying you want to make the system as lossy as possible? Yeah, I'm not sure how to do that. So here are my thoughts right now. So you'll eventually lose enough information, right? But that's the thing. So apparently, this actually turns it into a pretty good story when you think about it, because apparently people are using fractals to do image compression anyway, right? So that means it's actually a pretty good compression method. So what we could do at the start is I could snap my fingers and it's literally the same image, but like you do image to almost literally the same image with a little bit of compression. And then the question is no longer like, how do I become a fractal? It's now like, how do I lose enough information that I actually look like a fractal, even though I already am a fractal, right? Like, so I snap my image in my hands and I'm like, I promise I'm a fractal now, but like, I have to, okay, here, the paper may seem like some kind of super resolution, but that can't be right. No, it's not super resolution, right? Again, so what they did is, I'm sorry, when I said this is a compressed image, I said this wrong. You're correct, I said this wrong. So what they did is they took the image input, which looks like, I'm sorry, I did a bad job of explaining this. They took the image input, which looks a lot like this guy, and then they made the image smaller to this guy. Oh, okay, they took this image, and they created a set of functions that will create that image, right? And then they said, okay, so now we can compress the image. And so what they did is they made the image a quarter of its size by turning it into this weird pixelated form. And then after turning it into the pixelated form, they then used the functions to recreate the image. So that image up there, this image is the compressed image, but it's after they've already created the functions to go from one to the next. Does that make sense? So it's like, the idea is to store a smaller image on their system, right? So they still store an image. It's a fourth the size of the other image. And they use that compressed form into the input that they've given. They use that compressed form to generate the new image. So they just go back and forth. So the pixelated one is the intermediate form. Yes, exactly. It's the intermediate form. Yeah, that's the best way to put it. So in order to restore it, you would have to store the compressed image and the functions. Yes, that's exactly what you need. You need to store the compressed image and the functions to recreate the compressed image. That is exactly what it is. And so I think an intermediate form is a better way to put it. Okay, so yeah, so now the question, so again, this is a good question to have. And I'm very glad that we went through this because honestly, like last night, I don't know, basically super pixelated form plus functions in normal image. Yes, that's what it is. Okay, so this is actually really cool for a number of different reasons, right? So the reason this is now cool is because now we can take any image and we can turn it into basically a set of functions, right? But here's my question. Can we, okay, and this is a stupid question, but it is a question. I'm not saying it's the best question. Can we not keep the image and can we only keep the set of functions? Okay, that's my question, right? So as we said before, the way this works is, actually, let me write it out in the way that you guys have just written it out. We take an image and we turn it into a small image plus a set of functions, right? And so my question is, could we potentially take an image and make it so we don't have to keep the small image at all, and we just keep the set of functions, right? So we basically put into the fractal generation method, put into that Hutchinson operator that we create for the fractal compression, a set of random inputs that then recreates the image. Instead, would that work? I don't know. That is what I was thinking in the beginning when you were explaining what you were doing. That's what I thought it was, but I was actually wrong. And so the fractal compression is different than what we wanted to do, which would be really cool, I think. You should be able to assume 0 as an input. Right, I think that's true. I think we can assume. So that's our goal. Our goal is to make it so we only have to keep the set of functions. That would be like, that's compression for you right there. Like, it's going to be, we're expecting it to be super lossy, like incredibly lossy. But who cares? Like, I think that's cool. I like that idea. So I think that's what we're going to go for. So I think the steps to do this, let's go ahead and outline the steps to do this, because there's a lot. I'm kind of wishy-washy on what we need to do. So obviously the first thing that we need is a good implementation. So a good implementation of iterated function systems on GPUs, right? On GPUs. That's one thing that we have to do, which is a problem we're hopefully solving this week. The next thing that we need to do is probably an implementation of fractal compression. Of fractal compression, right? Just to try it out, see how it works, and to make sure that we can make it work, right? The next thing that we need is basically once they have the fractal compression in here, right? The way that they do it is they kind of have a set of affine transformations that they work with. So then what we want to do is extend that implementation of fractal compression to an arbitrary, we'll say fractal flame set. Fractal flame set is what we'll say, whatever. So essentially the idea is, just to kind of make sure everyone's on the same page, the first thing that we have to do is have an implementation of iterated function systems on GPUs, and the reason we want that is so that we can do this quickly, right? Because we're going to have to iterate a bunch. The next thing that we want to do is create a simple implementation of fractal compression. Easy enough. The next thing we want to do is make it so fractal compression works on an arbitrary fractal flame set. And then finally, we want to put it together so that our error here, finding the root mean squared error, works with, so then we want to do some sort of optimization. So that we can, minimize the root mean squared error, right? So this looks like, it's a week or two out is what we're looking for. I read that some researchers generate images based on deep learning AI that is overtrained on one image and save only the weights, but having an algorithm only for one picture is useless. I mean, an image is just one big piecewise function. You guys, yeah, you're totally correct. Like, I'm not sitting here and trying to, like, this is the nice thing about being an independent researcher. The stuff you make doesn't have to be useful, right? You just make it, and it's like, here you go. Push the boundary of human knowledge. No one cares, but, here I am pushing it over here in the corner. Like, who cares if, like, the thing you're doing is citable? Who cares if the thing you're doing is actually useful? Sure, this is definitely going to be, like, the worst compression method. Well, it'll be fine. Like, who cares? It will be a compression method. But, like, I'm not going to argue that you should use the compression method. I'm saying it exists. And it exists because of us, and that's the cool part. Like, and I think, like, that's the thing that I've always wanted in research. Like, I never really cared about whether the thing is actually useful or not. In fact, for the most part, I like things that are not useful. It's just the fact of doing that one little thing that's just like, it's an interesting problem, let's solve it, Yeah, that's the thing. I'm really pushing for that now. Like, the thing, I mentioned this at the start of stream, but there was a long time, for the past 2 years, where I've done, like, no research. And, like, in my mind, I've always wanted Laos Labs, and I always wanted to be an independent researcher. That's what I've been wanting to do for years. And now I'm just like, just do it. Just freaking do it. Don't let your dreams be dreams, man. Like, just, get out there and just, like, try your best. And if it fails, it fails. But I mean, right now, you're at a stage, you've got 75,000, or I've got 75,000 subscribers on YouTube. I'm making enough money as contracted work that I'm doing okay. So let's just do it and, like, quit being quit holding it off until the next day, Yesterday you said tomorrow. Right, that's exactly right. Like, and I just need to be like, I just need to do that thing. It's something I want to do. Just, I have the ability to make progress towards where I want to go. Let me do that. Cloud Giant, thank you so much for following. Really appreciate it. It's a risk. My life right now is constantly in flux. I don't even know where I'm going to be this summer, let alone, next semester. I'm, like, completely lost for the next few months. But I've got a stable enough job and I'm doing okay. So you're strong independent researchers that don't need no university. Anyway, so I think as far as problems of the week, I think our problem of the week for this week will be this guy. The problem of the week for next week will be this one. Problem of the week for the week after that will be this one, and then this one. And there's going to be a few problems sprinkled in there. So it looks to me like we're going to be able to get the whole project done in, like, 6 weeks. That's what it looks like. Which is good. Like, honestly, that's pretty good. If we can really hammer this out, I'm going to be incredibly happy to get this all to work in 6 weeks. Okay, what I'm going to do for the rest of this hour is I'm going to spend a little bit more time just reading up on fractal compression, just to make sure that we do actually adequately understand it. I'm going to go back to the Wikipedia article, which was structured slightly differently, and then we're going to hop on to actually tackling problem 1 here. Now, it is 5 o'clock p.m. my time, roughly, which is fine. I think I can go until maybe 6 or 7 this afternoon, so I'm not really sure how long I'll be streaming. But again, if you like this type of content, my plan is to be streaming like this more frequently from now on. I mean, I've got a meeting from 3 to 4 tomorrow, but I'm going to be trying to stream as much as I can. I might, like, split tomorrow into 2 streams. No, 7, I should go to bed at, like, 7 p.m. Like, I'm a wimp. Like, my sleeping schedule right now is, like, 7 p.m. to 3 in the morning. Like, that's when I sleep. Sometimes I can stay up until 8 or 9, but, like, anything past that is just, it's hard. Oscar Oscar Rallian, thank you so much for following. No, Oscar Rallian, thank you so much for following. Really appreciate it. Final ramble note before continuing. I really do think that this idea of like really showing research online, people haven't done it before, and I don't see why not. So let's just try it, and if it fails, it fails, you know? I'll pop in and out. I'm supposed to be doing a graphics project myself. Yeah, good luck. I mean, being up at 3 a.m. is not wimp territory. Let's be real. I go to sleep. I go to sleep when you wake up. My roommate actually goes to sleep about when I wake up. So we sometimes have like completely contradicting schedules, you know? There have been a few days when like he's gone to bed at like 1 or 2 a.m. and I've gotten up at 1 or 2 a.m. It's definitely happened a few times. But yeah, I will be trying to stream more frequently. I say that a lot, but I do actually mean it this time. And I mean it every time. So, you know, like, who knows? But the point is, like, essentially yesterday, I did just a little bit of research. It had been years since I'd sat down and just read an academic article, and I forgot how much I love it. Like, genuinely speaking, there's nothing I enjoy more than just, like, reading papers and just, like, piecing things together and like trying to do things. It's just, you know, trying to do things that no one has done before. Like that is why research is cool. And like, sure, you can argue that we're not doing anything cool. Like people, you know, you could argue that the stuff that we're doing is not, you know, particularly novel. It's not pushing the boundary far, but just, it's still cool. Like the world's first this is still the world's first this, you know, even if it is the world's first implementation of this on GPUs, and it's so specific that like, you know, like it's hardly useful. That's still okay. It's still the world's first something, and that goes for something, you know? Anyway, I'm going to go ahead and keep reading the article on Wikipedia. Then we have 110 mountain climbers to do. And then we're going to talk about the spanning tree example. My goal by the end of the day, whether that's at 6 or 7 p.m., whenever we get there, is to basically suss out how we're going to try our implementation on the GPU for the Chaos game, and get that figured out by the end of the day. And then tomorrow, hopefully we'll come back and just start the implementation and see where we get. Again, the goal is just to finish one project every week, and I am going to be putting a video out as well. Thank you so much for the subscription, the Cherevi. How are you doing? For those of you guys who don't know, okay, I don't know how to say this, but Viterevi is a wonderful GPU programmer. He's actually the guy who created kernel abstractions in Julia, and we will definitely be using that, maybe not today, but probably tomorrow, as we start hopping into the topic a bit more. So I'm going to go ahead and put Simulcow in chat. And in fact, if you guys want, we can actually have him to talk about GPUs in Julia and stuff like that. I think we had that before, just randomly impromptu. But if you're, I need 2 Simulcows. But yeah, he's actually a wonderful Julia GPU programmer, so it's really cool. I need to watch. Oh no, I need to watch that to get user feedback. we might do that if people are interested. Of course, like at the same time, I don't want to pressure him to do anything that he doesn't want to do. But yeah, definitely on the in terms of like people who know what they're talking about, he knows what he's talking about more than a lot of other people I know. So. Okay, so we're going to keep reading more about fractal compression, and then after that, we're going to, we're going to hop into the next workout. Again, our 110 mountain climbers. I don't know if I have any push-ups this hour. 1 push-up, and then we're good to go. Here we are being tested. I'm going to sleep. It's quite nice to co-work with you guys. Yeah, thanks for being here. Adding another push-up. Thanks for that, Lord Lycon. Okay. So we're going to keep going. So the last part that we read for this particular fractal compression on Wikipedia was for binary images. The extension to grayscale was what we talked about with the Barnsley article, whatever. I guess we're going to read the encoding bit and then, yeah, see what we can do from there. So encoding, a challenging problem of ongoing research in fractal image representation is how to choose the function f of 1 to f of n such that its fixed point approximates the input image, and how to do this efficiently. A simple approach for doing this is the following partition iterated function system. Okay. This is something that I should probably read more about. Why do chaos games suck on GPUs? It's because chaos games are inherently iterative, and there is no... there's a lot of reasons for it, but because they're inherently iterative, there isn't really an easy way to turn them into a parallel form. specifically because the minimum like number of elements the GPU works on is known as warp, which is basically 32 elements. And so even if you have like a huge array of things that are all working iteratively, you still got to kind of shuffle the array or do some sort of weird thing so that those 32 elements are not all going to the same location. Yeah, exactly what V said. Okay, so we partition the image domain into range blocks of Ri size S by S, and for each Ri, search the images to find a block D of I of sizes 2 of S to 2 of X that is very similar to R of I. And then we select the mapping such that H of D, H must be the Hutchinson operator of D of I is equal to R of I for each I. Right. Sadly, there's still a lot of fields of science that cannot be parallelized at all. Oh, definitely. That's definitely true. In fact, I think some of the stuff that you work on, you do, didn't you say that you used to do protein folding? No, I feel like that's relatively parallelizable. But there's definitely some stuff in computational chemistry that's like very, like almost impossibly parallelizable, you know? Also, by the way, hey Crophead, Vexatos, everyone else, thanks for coming in, guys. Appreciate it. Okay, so I have no idea what I just read. I'm sorry about that. So we're going to have to read it again. Okay, so a simple approach for encoding is the following partition iterated function system. So 1, we partition the image domain into ranged blocks of R of I of size S by S. That is exactly what we saw before, where they split the image up into 4 by 4 blocks. And then for each R of I, which is each ranged block, we search the image to find a block D of size 2 of S by 2 of S that is very similar to R of I. That's the bit I'm not sure about. Okay, so let's try to figure that one out. Not that I don't like GPUs, but have you ever thought about using FPGA for that? Okay, every single time I try to use anything with FPGAs, I just get confused, you know? I definitely did not understand why GPUs doesn't get it. Well, actually, okay, so Crophead, after this hour is done, we're going to hop into it again, and we're going to talk about why it's iterative and stuff like that. So next hour, we'll talk about that. That was why I kind of hand-waved it away, but we will talk about it soon. It's just a matter of time till we get there. Some things are provably unparallelizable, definitely. I don't really get how you can parallelize differential equations. Usually what you do to parallelize differential equations is you have some large domain that you iterate over. So like you have a 2x2, maybe, not 2x2, but you have a 2-dimensional, 3-dimensional, 4-dimensional grid, and you apply the PDE essentially to each element in the grid. So you parallelize over the grid instead of parallelizing over the solve. That's usually what you do. Which is, it still works pretty well. It's just that there's some solves that are just particularly bad, and that you just kind of stay away from if you want to do it in parallel, you know? Actually, it's kind of interesting that the difference between CPUs and GPUs means a lot for PDE solving. A lot of times it's actually better to do something over a group of CPUs, because CPUs are a bit chunkier and can do some of the iterative processes better than GPUs can. It really just depends on the system. But I think GPUs beat out this was 10 years ago. I think nowadays GPUs beat out most things. Or rather, they've ported all the stuff that doesn't work very well on GPUs to GPUs now. It's been a while since I really delved into that literature. Okay. What do we have here? So we say for each R of I, which is a ranged block, we search the image to find a block D of I, of size 2 of S by 2 of S that is very similar to R of I. And then we select the mapping function such that H of D is equal to R for each I. In the second step, it's important to find a similar block so that the iterative function system accurately represents the input image. So a sufficient number of candidate blocks for D of I need to be considered. Okay, here's my understanding. On the other hand, a large search considering many blocks is computationally costly. This bottleneck of searching for similar blocks is why partition iterative function system fractal encoding is much slower than, for example, DCT and wavelet transforms. I'm sorry, I'm hiccuping. The initial square partitioning and brute force search algorithm presented by Jacques, I don't know, provides a starting point for further research and extensions in many possible directions. Different ways of partitioning the image into range blocks of various sizes and shapes, fast techniques for quickly finding a close enough matching a domain block for each range of block rather than brute force searching, such as fast motion estimation algorithms, different ways of encoding the mapping from the domain block to the range block, etc. So this is the interesting bit. So what they're saying is essentially, if you look at this image over here, basically they took an image that looked like this one, and then they turned it into these blocks, and then they use the fractal compression to basically turn it back into an image that looks like this one. So their input image was basically a balloon. They compressed it into these 4x4 range squares. And then what I didn't recognize in this paper is that the root mean squared error here was actually being used to compare each of these blocks to its corresponding block in this image, right? And so what they're trying to do is they're trying to figure out, you know, where this point should exist in the function space. Like, so let me try to do this. So this pixel right here. Oh, that was a dumb circle. This pixel right here. The question is, where is that pixel best used in the function space to generate essentially this set of pixels or the corresponding set of pixels in the image? And so what they're doing is they're basically trying to like go from, you know, the compressed image to the other image. And the question is, how do you do that? And that's what the partition iterated function system is for. Now, here is where our stupid method, where we don't use any type of compressed image and we just save the functions, might win out, because we don't have to do this. We just save the functions and we go with it. So our stupid method here might win out. If we can make our stupid method work, then our stupid method isn't the stupid method anymore, it's a smart method. But the problem is it's going to be stupid because we're stupid people. But eventually, well, I'm a stupid person. I didn't mean to extend that to you guys as well. I know the method isn't going to be great, but it's fun to try and see where we go, you know? I love listening to smart people. Yeah, there's probably a whole bunch of smart people streaming on Twitch right now in the science and tech category. Basically every stream except for mine. Publish it and call it the Schloss stupid method. Stupid fractal compression. Anyway, it's super fun. Like I'm actually really excited. Again, the nice thing about doing this here on stream and with you guys is that we don't care about novelty. We can just do whatever we want. There's some kind of learning the fractal function for each image. Right, exactly. Come on, give yourself some credit. Okay, maybe a little. Makes me interested to see what happens if you feed a different compressed image into the operator. Exactly. That's why this question here, implementation of fractal compression, the actual question that we're going to solve that week is, the question for that week is not like what is fractal compression. It's like fractal compression, with weird inputs. That's the question for week 2 that I'm actually incredibly excited for, like really excited for that one. I actually learned here more here than I do on other streams. I'm fed up with people telling me what is a for each loop. We definitely don't explain what loops are, partially because if I try to, I'm certain someone in chat will tell me I'm doing it wrong. So you want to generate an operator for an input image, then try the operator on other images. Exactly. That's going to be next week. Trying to figure that out. This week's problem is, again, just implementing iterated function systems on GPUs. That's this week. Next week's question is going to be something else. I like this idea of just kind of doing a different problem every week and just seeing where we go, you know? Okay, let me finish up this section on the encoding scheme. I don't think we necessarily need to talk about this stuff here, because this is stuff that's going to go in one ear and out the other. And I think that's going to be a question for next week when we actually do the implementation of fractal compression. I think the discussion of fractal compression should basically end at the end of this hour. Let's see. The initial square partitioning, right. So other researchers attempt to find algorithms that automatically encode an arbitrary image as RFS recurrent iterated function systems or global IFS rather than partitioned or iterated function systems. And algorithms for fractal video compression include motion compensation and three-dimensional iterated function systems. Fractal image compression has many similarities to vector quantization image compression. Okay, let me see what these guys are talking about. So I am going to see when these papers are published. For the most part, it looks like most of this was done in the 1990s, and no one has really touched it since then. So what I'm going to do is I'm going to go to Google Scholar over here. We see fractal image compression cited by 491. And let me see if there's anything since 2021. There's one paper since 2021 on the F-transform preprocessing for JPEG strong compression of high-resolution images since 2020. How many do we have? Anti-Mandelbrot sets via JunkM iteration, a review of contemporary image compression techniques and standards. Fair enough. I don't know if it's considered contemporary anymore. Image compression using principal component analysis. Well, that's an interesting one. Optimizing fractal encoding using cuttlefish optimization. Cuttlefish optimize. What does that mean? Cuttlefish optimization algorithm? Are you kidding me? Like cuttlefish optimization. What? Cuttlefish algorithm. What is a cuttlefish? I'm sorry, 1 second. Cuttlefish algorithm, a novel bio-inspired optimization algorithm. Do you have any plans yet on GPU-fying compression algorithm like this? A cuttlefish is related to a squid. Fair enough. Did I add the push-up Lord Lycon? I don't remember if I did. I'll just add another push-up. That's what I was thinking. But no. Oh no. Oh, this paper has everything. It's got like weird biological images that are hard to understand. It's got MATLAB plots. Oh no. Oh, it's fine. I'm sure it works. I'm sure it's great. But like, it's fine. Let's see. What do we do here? Let's go back. I'm going back to this guy. I just wanted to see like what people were publishing in 2021 to see like I think this field basically died like in 2000. Like no one really is using it that frequently. In fact, I'm sure if we look at the review of contemporary image compression techniques and standards, I'm like 90% sure fractal compression is just going to be used as a side note. It's going to be like, people tried to use this, but it didn't really work. Provad, thank you so much for the raid. Party 1, how are you doing? Thank you for that. Soding, how are you? Oh wait, party of how many? It says 1, but it's probably fine. Doesn't matter. Let's see. But yeah, I hope you're having a great day. How's your stream, man? What do we have? Also, if you guys don't know, Soding is another science and tech streamer. He's on pretty much every day that I'm aware of. Might have missed it a few days, but he does some amazing stuff. Check out their channel. They do some great stuff. If no one's using it, does it mean it's a bad idea? It doesn't mean it's a bad idea, but it does mean that people are not using it anymore. It doesn't. Again, it could still be a good idea, just not that people are using it. Let's see. I never heard of him. Never heard of him, and you use a Soding language emote. Please shout out Probot, not me. He raided you. I think I said thanks for the raid as well. And then I asked how stream was, but he hasn't said anything in chat. But yeah, definitely check out Probot's channel as well. I actually have not seen their channel, but I'm sure it's great. Let's see. Cool. I heard that he's a big Rustacean. Wait, what? Oh, Rust user. Yeah. Okay, so guys, we have 110 mountain climbers to do. And how many push-ups? It looks like 2 push-ups? 3 push-ups. And how many push-ups can you do max? I don't know. Like, I don't count the max number of push-ups. So we're going to go ahead and do the push-ups, and then the mountain climbers, and then we're going to move on to the next question, which is going to be how we want to do the parallelization for the iterated function system. Yeah, we're going to see how that goes. 110 mountain climbers might be a lot, so we're going to see how that goes. Probod's porting open source Half-Life 1 engine to Vulkan. Oh yeah, super cool. Yeah, I'm happy to hear that. So if that sounds interesting to you guys, which I'm sure it will sound interesting to a lot of people here, definitely check that out. That's really cool. Okay, reward is on cooldown. It'll be back in 24 seconds. If you want to add a push, I'll do an extra push-up then. That sounds fine. Okay. So we will, I'm going to change the microphone location. We'll hop onto the push-ups, do that. For those of you guys who might not have been here on the channel before, the idea is that we do basically a 5-minute exercise and then a 55 minutes of just project working on something every hour. It's a way to break up the monotony. It's also a way to keep me motivated and energized to just keep going with the stream and to keep everyone else just excited and like, get the blood flowing and maybe get people to get up from their desk and do a little bit of exercise and stuff like that. Let's see, what do we have here? Lord Lycon, thank you so much for the extra push-up. I'll go ahead and add that in. And that's where we're at. Unfortunately, Provod, you definitely came in on stream at like a really weird time. Like we're about to do the workout set, so I do apologize for that, but hey, I'm happy you're here. My stream is okay. Vulcan got to draw something with broken layout alignment. Yeah, cool. Okay, yeah, but definitely check out the stream if that sounds interesting to you guys. I'm going to change the microphone location. We're going to do our quick workout, and we're going to get back to fractal image compression. Actually, we're going to get back to GPU-ifying iterated function systems after that. So, yeah, be right back. Oh, 1 second before hopping off. Increasing the difficulty it would increase the difficulty of the mountain climbers. You can do that if you want. However, 110 mountain climbers is already a lot. I realize I'm going to be the one doing it, not you guys, but, you know, like, it is what it is. Okay, be right back. Okay, so for those of you guys who, 1 second, I'm all over the place. What's chat say? I don't know, how's that exercise? Oh, you'll see. Okay, so how many push-ups do I have? 4 push-ups, and then 110 mountain climbers. So for those of you guys who might be here or watching from home, the idea here is not that we, you don't have to do 110 mountain climbers. You don't have to do 5 push-ups. The idea is just to get up, get the blood flowing, walk around a little bit, and just kind of get up off the chair and you know, kind of refocus yourself for the next hour. So that's the idea. I'm going to go ahead and do the 5 push-ups and then the 110 mountain climbers. 110 is a lot of mountain climbers. You'll see in a second, but it should be doable, I think. So it should be fine. All right. 5 push-ups first. 1, 2, 3, 4, 5. Okay, let me make sure I'm on frame. I think I am. Perfect. Okay, now for the mountain climbers. So I think Redu said that he hadn't seen mountain climbers before. So what I'm going to do is a set of 10 mountain climbers. Sorry, the microphone's here. So what I'm going to do is a set of 10 mountain climbers first, just to show how it's done. And then I will do a set of 2 sets of 50 mountain climbers. That's what we're doing. PH1GO, thank you so much for following. Really appreciate it. And yeah, so let's go ahead and get started. So what you do for mountain climbers, for those who might not know, is you basically get in a plank position like this. And then basically you just move your foot up as fast as you can. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's a mountain climber. That's the first 10. And we'll just do a set of 50, 2 sets of 50 to make it so we're at 110 mountain climbers total. I could do that. Yeah, it's actually pretty easy. I recommend if you haven't done it before, do, I don't know, maybe not 50. 50 is actually a lot. Maybe a set is like 2 sets of 30 or something. I'm not really sure. But it does get quite tiring after a while. Remember, you're holding that plank position and you're also moving your legs really quickly. So yeah, we'll go ahead and get started. Maybe 5 seconds, 10 seconds of rest. So we'll be going in 3, 2, 1, and set of 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 3, 4, 5, 6, 7, 8, 9, 10, and 5, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are tough. That's okay. So we've got another set of 50. I think I was doing those actually kind of fast. I used to do mountain climbers like more as like a lunging operation, but I kind of stopped doing that ever since I started playing Ring Fit. The mountain climbers in that game are really hard to get like accurate, so now I have to like do that specific mountain climber technique to make it so I can actually like, you know, get it to register in the game. So okay, one more set of 50, and I think we'll be good to go, and we'll get back to the programming. All right, we're gonna go in maybe 5-10 seconds. Well, no, we'll just go. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, sets of 50, 110 mountain climbers total, and now we're just gonna get right back to the programming. Okay, what do we have here? Pablo the Best, 10K, thank you so much for following, really appreciate it. Give me just a second, I'm going to change the microphone setup, and then, yeah, we'll be good to go. Give me just 1 second, guys. I'm gonna move the chair around. Oh, I'm also breathing really hard. Oh well, it's fine. And also let me move this. Sorry, you guys might be hearing that in the stream. And one other thing. I want to do this guy and turn this off, turn that back on. Okay, so we spent the past few hours talking about fractal image compression. We're going to put a knot in that. What's the phrase I'm looking for? We're going to put a pin in that for now. Oh, and I also have to get the next set. So let me change the push-ups to 0, change the next set to be, this guy. Arm hold. We just did arm hold. I'm going to do that again. I don't understand how we got arm hold twice. Rollouts. Okay, rollouts seem fine. 55 is a lot. It's fine. I think all of these numbers are kind of a little bit out of whack. Let me get some water. And now we're going to talk about why chaos games in particular suck on GPUs. We introduced it earlier on stream, but there's a lot more to it. So, journal. New page before. Okay, so for those of you guys who weren't here earlier in stream, we could save that under, I guess I want to save it under Barnsley, just Barnsley. Save. See what that does. Alice here. Yeah, Barnsley.zop is what I'm looking for. Okay, so what I'm going to do is I'm going to go over here, Control D, CD, videos, algorithm archive, CD into iterated function systems, Alice here. And I'm just going to open up a video. So I'm going to open up the video of this one. So MPV, Sierpinski, Hutchinson. There we go. Okay. So what are iterated function systems? That's a very good question. Thank you so much for asking. Let's say we have 3 initial points, A, B, and C. And we create 3 new points, D, E, and F. I'll go ahead and color those guys in. Now what we're going to do is we're going to create 3 functions. One brings you halfway towards A, another brings you halfway towards B, and another brings you halfway towards C. The idea is that, each of these points, D, E, and F, will generate 3 children, and one of those kids will move halfway towards A, another of those kids will move halfway towards B, and another will move halfway towards C, right? And essentially, if you just run this again and again, where all those kids have kids, and 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 so on and so forth, you eventually generate the Sierpinski Triangle, right? And the reason this works is because it's kind of a hand-wavy explanation here, is that the function system, the set of functions that you go halfway towards A, halfway towards B, and halfway towards C, are called a Hutchinson Operator. It's a set of functions that when iterated through bring you towards an attractor. An attractor is a 2D image, and in this case the attractor is the Sierpinski Triangle. So the idea is that essentially we want to recreate this concept with on the GPU, right? That's what we want to do. Now, what we just talked about was iterating through a tree, right? The idea was we have one particular location in space, which is, which is this location here, where we start. And then, we have 3 children. One goes through F1, F2, F3, and those have 3 children, and 3 children, and 3 children. Now, the issue with that is that, if we have one huge, balanced tree that just goes bigger and bigger as you generate more and more kids, clearly this is computationally intense. Well, memory intensive, right? Because you have to keep the whole tree in memory, and it grows exponentially, and it's just kind of a pain, right? So we came up with a bunch of ways to solve this before, where we kind of iterated through a trit string and all this kind of stuff, which we'll talk about in just a second. But the normal way, which people do this implementation, is through something known as a chaos game. So if I go here and we use Sierpinski chaos, and we start A, B, and C, we generate the Sierpinski triangle, And then what we do is we create a random point. It doesn't matter where the point is. Here it's generated kind of in the center of the image. And the idea is this single point can choose any location to move to at random. So it can choose any function to use, function 1, 2, or 3 at random. So here it chose to do function 3, move halfway towards C. Then function 1, move halfway towards A. Then function 3 again, and then function 1. And then it decides, oh, I'm going to move halfway towards B, and so on and so forth. Right, just kind of picks a function to go along. And eventually it finds itself on the Sierpinski triangle. I didn't have to show this many points, but maybe around, this point in here or so, you could clearly tell that it's kind of on that triangle. And once it's hit that attractor, once the point has been attracted to the Sierpinski triangle, no matter what function it chooses, function 1, 2, or 3, it will always be on the Sierpinski triangle, right? And that's kind of the beauty of iterated function systems. It allows for you to basically create these weird images, these attractors, by basically picking a point and just randomly having it move from point to point. So now the question is, why does that suck on GPU? Why is that awful on GPUs, right? That's the question. And it's not obvious as to why. For people who don't know GPU engineering, or people who maybe don't know fractals so well. So again, we're going to start with the chaos game description. Chaos game. Because that's the one that has a lot of promise. People have moved this to GPU systems before. And I'm going to explain why that method sucks, and why we need to do better than that. So, right, so if we start with point 1, we're just going to give it a point. What we're going to do is we're going to choose a random function, fn, f of I, where i's, within, 1 to 3, 1, 3, or something like that. Then we have a new point and we choose another function I, and then we have a new point, we choose another function I, and so on and so forth. Essentially what's going on, is that we're choosing a random point, and then we're applying a function to it. We're choosing another random point, we're applying a function to it. We're choosing another point and applying a random function to it. Confused by the question, legendary, because I think that's what I'm doing. So if something's unclear, please feel free to ask. And so the idea is that we're iterating through the function system by basically taking a point, applying a random function to it, taking a point, applying a random function to it, taking a point, applying a random function to it. And this is inherently iterative, right? Because it relies on the point's previous location at every step. So it's hard to parallelize because you can't just say, I'm going to do this step independent of this step over here. You have to do them in order, right? And because you have to do them in order, this means that this is just not going to work very well on a GPU, because a GPU works inherently in parallel, right? And there's some other limitations here that we have to talk about as well. So what is a GPU? That's a good question. Thank you so much for asking. A GPU is a graphics processing unit. I'm sure a lot of people here probably know what it is. You can convert them to I matrix operate. Even if they're I matrix operations, that doesn't solve the parallelization issues, I don't think. But I'll explain how people normally do it in practice and how to get around this. But you actually get a point on the attractor, or just arbitrarily close approximation. In principle, in practice, it's an arbitrarily close approximation. But you still get you essentially get the attractor out. Okay, so for those who don't know what a GPU is, it's the thing that basically displays the graphics on your screen. So if you have a 1920 by 1080 image that is being displayed on your computer at any given time, that's like, 1 million, 2 million pixels that are being generated basically every 60th of a second. And that's, what your GPU is doing. So it's really good at doing like small bits of computation, like, pixel color flipping and stuff like that, but doing it really quickly, right? And so it kind of just batches that screen into a bunch of little boxes and does a lot of the operations in parallel, a lot of them at the same time, to do the operations as fast as possible. So some things are super good on GPUs. Some computation ends up being really fast on GPUs. If you can split it up into these little itty bitty tasks that are completely independent on other tasks. That's not what the chaos game is. It inherently relies on other pieces to be fed into it. Are these points always the same point or random point at each setup? This initial point is random, but every other point in the chain depends on the one before it. So in principle, it's a random point for each. No, it's a random point initially, and then the point depends on its previous location. Is an attractor kind of limit of a figure sequence? Yeah, you can think of it as a limit of where the point goes to. We use many points on the GPU, right? Right. So this is the issue, right? So if you use 1,000,000 points, you can parallelize that way, right? So let's talk about that parallelization. This is why it's actually bad on a GPU. So obviously the next question is what CropWeb came up said is, okay, fine. If you're using a GPU, clearly, you can't just use 1 point and move it around. What you want to do is you want to use 1,000,000 points, and you want to segment your operation so that it works over those 1,000,000 points instead of working over just 1 point that moves 10 million times, right? The issue with this is the following. So if you have, let's say, let's just say we have, 8 points. So here's 8 points, right? The minimum level of parallelism for a GPU is something known as a warp, which is 32 threads. This means, by the way, Gaga Blog, thank you so much for following, really appreciate it. Which means that it executes basically 32 elements at the same time. So you can't single out this guy and say, we're going to apply function 1 to that, and then this guy and say, we're going to apply function 2 to that, or this guy and say, we're going to apply function 3 to that. That just doesn't work on a GPU. Instead, all of these guys would all be given the same function, right? And that's the trouble here. Figuring out how to work outside of that warp group is the problem. So what people will typically do is they will say, okay, well, we have this group of threads here. And let's just say for the sake of the argument that the warp here, instead of being 32 threads, is just equal to 2 threads, right? So what they'll say is the following. They'll say you have maybe function 1. Function 1 applies to this space, function 2 applies to this space, function 3 applies to this space, function 4 applies to this space. And then what they do, make all elements calculate all functions, and then pick a random result. I don't think I've seen that solution before, but what people will do is they will basically make it so matrix element 1 and matrix element 2 will always be applied to function 1. Matrix element 3, matrix element 4 will always be applied to function 2. 5 and 6 will always have function 3 applied to them. 7 and 8, sorry, will always have function 4 applied to them. But every step, what they'll do is they'll shuffle the array, right? So that's what they do. They basically have this array, and they make it so this segment always has function 1 applied to it. This segment always has function 2 applied to it. And then they just shuffle it so that they can get around that warp problem. And that's what people will typically do. Now, the issue with that is that the shuffle is super slow on the GPU, because what you're going to have to do is you're going to have to do data transfer. From basically different global memory banks, and just doing that is undoubtedly the slowest part of your computation. So this is kind of the issue with doing an iterated function system, doing a chaos game on a GPU. You have all these arbitrary limitations that the GPU places on you that is really difficult to overcome. Strix, hey, how are you? Make it on a quantum computer. I don't know. I know a bit about quantum computing, but I don't think that's the right tool for this job, because I don't have a quantum computer immediately available to me to use. I do have a GPU though that I can use, so that's kind of where I'm at there. It is a GTX 970 though. It's like a really old GPU at this point. I need a better one. Let me get some water. You see IBM on the cloud? I guess I could. But I don't think that's particularly relevant right now. And honestly, I'm not super excited about, again, I did quantum stuff for my PhD, but quantum information was never something that I found super interesting. It's fine, I'll do it. But it's of the interesting areas to go into, it just wasn't something I found particularly exciting, But I know a lot of other people do. A lot of people really, really like it, and they're like, oh, this is the coolest thing ever. That's just not me. That wasn't what I was interested in. RSA 2048 cracking is kind of what to worry about. Oh, right, because of the quantum computation. I mean, again, I've done a bit of it. I've done, Shor's method and Grover's method and stuff like this, but I honestly, I never really got too into it. I really should have gotten further. I should, be better at implementing quantum algorithms and stuff, but I never did. Can you get around warp divergence by staging through shared memory? See, that was the question, and I don't know. And this is something we were gonna have to look into. But I don't. Okay, so here's where, if you can write all functions as a matrix, you could pick a random matrix and multiply. If you can write all functions as a matrix, you could pick a random matrix and multiply, right? But the multiplication still has to happen across a warp, right? And that's a big limitation, I think, because you one second, yeah. So actually, I don't know how that works. So between what Vichervi said and what Kropotov said, essentially, you know, we could create a shared memory tile here. And on the shared memory tile, we can put different matrix elements. So here we have, you know, whatever. Here's our shared memory tile. And, you know, the matrix element, we probably need like 6 or 7 matrix elements because it's an affine transform. So you probably need 6 matrix elements per transform. 9 matrix elements through transforms. And then you want to... Is that the idea? Actually, I don't know TPU so well. I should know them a lot better. So what we could do is we could segment these 9 elements to be some matrix, which we'll call matrix A, right? It has to be 3 by 3 because, again, they're affined. And if you watch the video that I just made on affine transformations, you'll see that it's usually done via an augmented matrix approach. We could limit it to 6 elements instead of 9, but typically it's done via 9 elements. So we have the affine transform here. And what we'd need to do is we would need to... Oh gosh, so these are going to have an XYZ location associated with them, so XYZ. And so we would make it so we have A, and then we'd have another 9 elements over here, which would be, you know, A2. And we could then, yeah, we might be able to do that matrix multiplication. I'm just trying to see if that would actually work. Because essentially what we want to do is we want to take some 3 by 3, 3 by 1 array, and we want to multiply it by this group in shared memory is essentially what we want to do, I think. That's what we're looking for. And then we want to take the next 3 by 1 array and multiply it by this group over here is kind of what we're looking to do. If we were to do it that way. That's about the best I can think of. And that would probably, but I don't think we have enough shared memory to do that because we have like 1 million elements that we're working with. You know, there's no way we could do that with a shared memory tile, I don't think. We could have it in global memory, though, and that would work. But I still feel like that's a lot of data, or a lot of memory that we have to keep for something like that. So I don't think that's necessarily effective. So, right, Kropotov, you said if you write all functions as a matrix, right? So the question is where do those matrices live? And, you know, how do you do that matrix transformation? I think you guys are right that you could keep all of the matrices in memory. You just provide 4 matrices as uniforms. You just provide 4 matrices as uniforms. So each of your functions, 9 by 9 matrices, you can put into constant memory. Right, but then, yeah, but that's the thing. The selection of, okay, this is what I don't understand, right? So my understanding is that if you were just to keep 4 in memory, right? And this is where maybe I'm wrong, but if you just keep 4 in memory, I don't think you get over the warp issue, right? Because you would still have to apply, if this is an F1, this is now A1 or whatever, to this warp, right? You still have to apply it to a group of 32, right? Because the selection, you can use pseudo random numbers to decide the matrix, right? But the question isn't deciding what matrix. It's that matrix has to apply to a certain group of functions, right? Like the issue is that application of the matrix would then. Okay, I don't understand how we could choose within a warp of 32 elements. I don't understand how we could choose. Is F1 expressed? Yeah, you can express F1 as a 3 by 3 matrix. Yeah. So what you'd want to do is you want to make it so this element here has F1 applied to it, and this element here has F2 applied to it. Let me redraw this so it's a bit cleaner. You're on page 4. So we have these 8 elements. And you want basically matrix 1, also F1, to be applied to this one. Just a single element, right? And then you want matrix 2 and F2 to be applied to this element. And I don't know how to do that because all of these guys are in the same warp, right? So each element is a 3 vector. Yes. So that's what I was saying. I was saying that if we had it so all of the 3 by 3 matrices were in one big array, I could imagine that working, right? Because if it's all in one big array, then you could do, you know, the batch multiplication. But I don't see how you could possibly do it so that you select one. You could use the coordinates as a source of random. Oh, maybe. Yeah, you could use the coordinates as a source of the randomness. For warp divergences, the important thing is that all threads need the same operations. Right. So that's why I was saying what Crophead was saying. Right. So exactly, the loads could diverge. Right. So the question is, how do you get it to point to two different locations in memory but have the same operation is the thing. And I didn't know how to do that because the selection of the random point would be done. The selection of the random array or the point in memory that you're going to seemed to me to only be able to be done at like the functional level, if that makes sense. But yeah, you're right. If we had another set of random arrays or random elements that we worked through, I think that's doable. Pretty sure that's doable. But here, so we were talking about this earlier, and there's another method here that we're not talking about yet that I think might also work and is something that I wanted to suss out as well. So have a good night, everyone. I can't pay attention to this. Anyway, Sierra, do have a wonderful evening. I hope that you have a good evening. I don't know. Okay, so we kind of showed earlier that if we have a tree, right? We can iterate through the tree by going through, in this case, bijective trit space, right? This is something that Crophead and I actually helped out with a while ago, right? So essentially, if we wanted to go through all possible operations, right? Essentially, we just go through all elements of a string, right? So we have 0, 1, 2, 1, I don't know, just like here we have, that was not random, but we just have a random set of operations here. And this means we go down this route here. So we go like down, the first one, the second one, the third one, the middle one, the third one again, and then this one. So the idea is that these are kind of directions to go through the tree, right? And essentially what you're trying to do is you're trying to go through as many of these locations as possible. So what I was thinking of, and maybe this isn't the best idea either, is that maybe instead of iterating through the points in space, we just iterate through this string and we try to find, I don't know, this is where I'm kind of lost and I don't know the best way to do it. And again, we're still running into the same issue where like, how do you pick randomness? How do you go around this whole warp issue and all this kind of stuff? We're still running into the same issues. But essentially this holds the entire fractal in it, right? And so the question is, how can we use that effectively? And I don't know that either. So this is kind of where I'm a bit stuck and I just kind of need to work through it and stuff. So my hope is by the end of, I think maybe I'll end at the top of the hour. Yeah, so I think we'll end at the top of the hour because again, I've already been streaming for basically 4 hours today. And I think that's a good way to kind of keep myself motivated and keep going. So I think that'll be a good place to stop. So I'm hoping by the end of the hour, we kind of have an idea of how to progress with this. An idea of where we want to go. So obviously we don't want to shuffle. And I think Crophead and Trevi are right that we can, we can still point them to different locations in memory. So I think this guy here, I think you can make this fairly performant if you define f to be a 3x3 by f of n, and then use device random numbers, a mod of fn. You define f to be 3x3 by f of n. What is f of n in this case? F of n mod f of n. If you define f to be, I see what you're saying. Yeah, I gotcha. It's 3x3. Duh, I'm done. By the number of functions. So 3, and then in the z dimension, it's a number of functions. Yeah, duh. Right. So then in the z dimension here, it's the number of functions. Yep. Functions. Oh, that's not how you rate functions. Whatever, it doesn't matter. Number of functions. Sure, perfect. And so then the idea would be, right. So then the idea would be you basically go through, and then NVIDIA GPU, you could use a non-coherent load. So that's where I'm a bit lost. Okay, but let's see. So we have 3x3 by f of n, and then we use device random numbers, mod of fn. Okay, so I'm a bit lost at some of this. So what we're saying is we have a 3x3 by the number of functions array. And so each vertical slice of this is going to be a separate function. So for example, for the Sierpinski Triangle, it's going to be 3x3x3. Okay, so then we're saying we have individual points in here, and whatever we do, we don't want to shuffle it. Like, we definitely don't want to shuffle this because that's going to suck. So how do we, and then we have device random numbers, right? Okay, perfect. So in order to go from one to the next, we can use, are the device random numbers going to be set in a separate array? Like, would we have, it doesn't matter, right? So as long as we have some sort of R&D value that is stored in some location, that doesn't split up the warp. So it doesn't mean that we have, you know, a divergence of threads doing two different things within the warp, right? It should be fine. Random number per thread in the warp. Perfect. So that's what we want then. So if we can get a random number per thread in the warp, then yeah, literally all we have to do is pick the random number. Yeah, do random number rand modulo the number of functions, which we'll call n, equals n. Yeah, no, that'll work. That'll work actually just fine. I like that. Yeah, that's fine. Perfect. Okay. I think that's good. So now the next question is CUDA.jl 3.0. Yeah, wait. It is currently, like, we could currently use CUDA.jl, right? Like, we could use what currently exists there to do this, right? Or am I wrong? Then on NVIDIA GPU, you'd need to use non-coherent load. So, okay, so that's where I'm lost. What is a non-coherent load? Exactly. As of this week. Fair enough. So that's my question. I should know what that is, but I don't. Let's just go back here. Just say non-coherent load. Does that mean, I don't know what that means. I'll wait for you to say something in chat so I don't say something stupid. Okay. So, LD, yeah, okay. Yep. Cool. Good. Okay, this is fine. So, let me draw this out. I'm going to save this notebook somewhere. So I just want to make sure I have this written down in a way that I'm going to remember tomorrow. So let's do journal, new page 4. The idea is that we have at const, right, perfect. So we have this guy, we have this guy. Let me just write this out in a way that I understand. For Pete's sake. So in here, we're going to have a function space. Each slice is a 3 by 3 affine matrix representing the functions. Whatever, representing the functions. A function. Perfect. And then what we're going to do is representing a function. Perfect. And then what we're going to say is to iterate through store a random variable number in each thread is what I'm going to say. And use that to, one second. Then you need to implement a theory with your matrix vector multiply. In theory, you could use static arrays. That should be fine. What about having a random matrix A, e.g. 4 by 4, so that A of I produces a set of random values? Wait, what about having a random matrix A, e.g. 4 by 4, so that A of I produces a set of random values for the ith block? I need to reread that one. Give me a second. A of I produces a random values. Oh, wait. So you're saying, I think, if I'm understanding you correctly, that would mean that each transform itself, by A to the power of I, I mean A to the power of I. So that A to the power of I produces a random. I need to think about that. Let's get back to that one in a second. I need to think about that one a bit more. Let me write down what I'm currently thinking of, so that I don't forget it, and then we can go from there. So where does the at const come in? So does the at const come in at the you said use, and you would need to use a non-coherent load. So where is the non-coherent load? Is the non-coherent load on the random number? I think it is. So iterate to store a random number in each thread. And we want this random number to be an at const, I think. At const. Sorry. Let's see, what do we have here? Minnie Jackson, thank you so much for following. Really appreciate it. And use that to select function. I'll say function per thread. Yeah, I think that'll do okay, honestly. I think. The non-current load is on the function array elements. Oh, right, because we only have a certain... Yeah. I see what you're saying. Because there's only so many functions available. We can do that. Yes. Well, since the index into that is not stable. Right, okay, yeah. I was just trying to think, like, in some sense... Okay, I'm going to say something dumb here. Do we have enough memory? Like, what if we have... What if we have a function system with, like, 25 functions associated with it? Do we have enough memory for that? Function array into shared memory. Right, that's what I was thinking. I was thinking it would be better if it was shared memory. I'm just going to put ... maybe shared. That's what I'm going to say. I think. And I'm just going to leave that there, put a question mark. I'm going to say that this shows me what I need to do to implement this method. Again, I'm going to save this and we're going to open it up tomorrow. Texture memory I'm scared of, honestly. I should, like, I'm just scared of using it. Like, honestly, every time I've tried to use it before, I've run into issues. I think because it's a float 32 and I was always doing things that depended on float 64 precision somehow. I think, if I remember correctly. I don't really remember correctly. Okay, so iterates through, store a random number. Perfect. Okay, so now let's go back to two other things that I want to talk about before we end today's stream. First of all, let me go ahead and grab this link here. Just see what that was. Over here, paste that. Perfect. Right, so I'm actually just going to create a text block over here. My PC is going to chug for a bit, and Control V. Oh, that's the wrong one. Control Z, text block, paste. Pete's sake. Grab this guy. Okay. Yank. And now we're going to Control V over here. Okay. I'm just going to have that available to look at next time we come in. I think if I just move out of the text block, I can still grab this, right? Yeah, I think I can. But it's big. Oh no. 1 second. How do I move that? Can I do this? No, that's not going to work. How big is it? Can I do the following? Can I do this? Control A? Okay, I can. Control X. Move this over here. Control V. Perfect. That'll work. I'll just remember to grab that next time. Okay, what do we have here? You could use texture memory. There's 64 kilobytes of dedicated constant memory. Although I don't know how to access that from CUDA.jl yet. Non-current loads are on global memory. That makes me want to use shared memory, but also I think we're going to implement this tomorrow. Today we're just theory crafting, so I'm relatively happy with that. So the next thing I want to talk about before continuing here, because I think this is a good way to go. I'm happy with that. I think it's great. The two other things that I wanted to talk about here was one, what Pavel the Best 10K was saying. I don't fully understand what you're saying. So by a to the I, I mean a to the power of I. So I here is what? Yeah, what is I? I'm so sorry. I don't understand it. So why do we want, so what is A? So do we want, so you're saying, what about having a random matrix A, e.g. 4x4? Oh, I see. You're asking so that we could put randomness into the system. That's what you're saying. That's how we get the randomness in. I is the index of the block we're currently processing with the warp. Gotcha, I understand now. So that's how you store the random numbers in the 4x4 A of I. So why does it have to be 4x4? Oh, I see. You're adding an extra, I see. So instead of a 3x3 array, it's 4x4 with a random variable associated with each element, right? So you're storing it all. This is going to be the matrix, if I'm understanding correctly. You're saying we have a 3x3 matrix here, and then somehow store the randomness over here on the last element? So A raised to the I meant A power of I. Okay. I think I'm understanding where you're coming from there. I is the index of the block we're currently processing with the warp. No, I got it. No, I understand now. No. I'm just dumb. I'm just dumb. You're saying we have a random 4x4 group. I got it. We have a random 4x4 group. Perfect. I understand now. 4x4. And if we do a raised to I, what this is going to do is it will give us 32, gives us 32 basically random numbers, which are modified based on I. And then we can use those 32 random numbers. I totally got it. I understand now. We can use those 32 random numbers in order to create this random number here that is used to select the thread. That's clever. Now, what VTRV was saying before was that we can probably store these random numbers in each thread. So, okay, let me write that down and let's think about that one a bit more. But no, I like that. That's clever. I like that a lot. 1 second. Okay. So potentially, I'm gonna say potentially to generate, let's see, 32 random values, 1 per thread and warp, 1 per thread and warp. We can do a 4x4 array, random array, and then we every step a raised to I is going to be equal to the random value for a raised to the I of I is going to be the random value a raised to the j of I is going to be the random value for each thread. I equals thread ID, j, okay, j equals warp ID, something like this. We'll work on that a bit. I mean, maybe block ID is a better way to do this, but it doesn't matter. The point is, we say warp, maybe block. Okay, perfect. This is good. I quite like that. This is nice. Okay, so now my next question is the following. Again, I think we'll end stream in about 15 minutes or so. CUDA.al uses constant memory for the seeds of device local random memory generator. The implementation is rather clever. What do we have here? Over here, there, open that, paste. L. You were saying the CUDA.al uses constant memory for the seeds of the device local random memory generator. That implementation is rather clever. I see. Okay, so okay, no. Yeah, maybe there's more to this. Okay, good. We have ideas. The only other thing I want to talk about, again, we'll be ending stream in maybe 15 minutes or so. The only thing I wanted to talk about before doing that is the following. So again, like we mentioned before, we can actually iterate through the entire iterated function system without keeping each individual point by actually instead iterating through a trit string, right? Like we said before. So if we have this trit string, my naive question here, trit string, right. So the question is, does this help us in any way? I want it to help us in some way because I think it's clever and I feel like there should be a way to do it. And what we could do is we could, for example, generate a bunch of random trit strings that we use instead of generate a bunch of random points that we use. And in this way, what we could do is we could, I think honestly we're running into the same problems. Even if every thread had a trit string inside of it, instead of having a point, a location, and like the question is, do we keep the trit string or do we keep the location in memory? Right. Now the difference here is that a location is basically an individual element in memory. So let's just draw this out. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So we have a tree. The location is specifically where each of these points are. So this would be the location. Whereas the trit string gives us the directions from one point to another point. So it gives us this to that. So this gives us the trit string, which I'm going to say is TS. So if we keep the location in memory, then we can effectively draw the iterated function system just by keeping a lot of points in memory and iterating through them and drawing them at every step. So that means our simulation is very time dependent because of that. If we keep the trit string in memory instead, this, I don't know if this actually helps in any way. I think we're running into the same issues both times, right? Because this doesn't help us overcome the warp situation. Because the question is, how do you act on multiple elements at the same time? The only difference is instead of applying a function here, we are modifying individual bits, which could be more efficient. The question is, what is the next bit? This is where I'm a bit lost. So like, for example, this could be 0, 1, 2, 2, 2, 1, 1, 0. I don't know, it's just a random string. It's not super random, but whatever, I can't do randomness. So obviously, if we wanted to get the full system, rather than iterating through the function system via the chaos game approach, we actually want to do a parallel traversal of the tree. You're right, string 0, 0, 0 is also random, totally random. My question is this approach that we just came up with for the chaos game better or worse than a parallel traversal of this tree? Of the tree, because we know the tree is always going to be balanced. We know it's always just going to be growing. We know what it's going to look like. No matter what the function system is, there is a way to iterate through it with this thing. And that means that we can keep a basically linear footprint. But I think I don't see a better way to do this via GPU. Like, I don't think the GPU helps us here. I mean, we'd essentially just get a bunch of random strings. I mean, what we could do is we could, like, for example, if this is our tree, we could get this element and like these elements over here or something like that. We don't have to go through the whole thing. We just have to get a relatively large span of the tree. You know what I'm saying? Which is what we're getting with the chaos game anyway. Like, the chaos game is just kind of picking some elements of the tree and it's just kind of showing those elements, you know? I think it ends up being the same. Okay. I think, though, this is a good place to stop it. We can do breadth first search with 32 queues, 1 queue per distance to root. Right, so this actually iterating through this trit string is already doing a breadth first search, right? So that's what that does. But it's counting. It's literally just counting. That's all we're doing. Surely parallel counting is easier to do than parallel. I'm thinking here. I'm having trouble with the whole thought thing. Surely parallel counting is faster than parallel iteration. You know? Like, you'd think it would be, right? And you're just counting all numbers. You're literally just counting all numbers to a certain depth, right? That's what you're doing. The limitations are... That's my question. That's my question. How... Let's say the trit string is 100 elements long, right? Or 1,000 elements long. A 1,000 element trit string is the equivalent of a 1,000 iterations element equals 1,000 iterations. Oh, just for Pete's sake. Okay, so the question is counting up to 1,000... No, it's counting up to 1,000 elements. And again, we're just counting 1, 2, 3, 1, 2, 3, 1, 2, 3. Faster than doing 1,000 iterations, 1,000 matrix multiplies. That's the question. So this ends up being basically for 1,000 elements. So this is going to be 3,000 additions plus a matrix multiply. Mult versus Yeah, I don't know. Yeah, so again, what we're doing is we're counting in function space. So the idea is 0, 1, 2, 2, 2, 1, 1, 0 means that you take some location and you apply function 0, well, you apply function 0, 1, 2, 2, 2, 1, 1, 0, right? So that's what you're doing. You're essentially just like going through all of the points, right? The occurrence of a case in a string. I mean, it doesn't have to be a string. I mean, I think there's probably a better way to keep it. Probably in the case of, like, you could probably just keep two bits, and you could probably do kind of count up with just the 2 bits or something. So the data structure that you're holding these in, it doesn't have to be too strong. And so then what you could do is you can turn all of this into one large matrix molt. So, and then we transform that entire structure of going through the tree into one matrix molt. Okay, and if that's all combined in one matrix molt, then what we're having is 3,000 additions to go through the entire tree, and then one matrix molt at the end. Whereas this one's going to have to do 1,000 matrix molts. Which seems... I don't know. I want to say that addition should be faster than the matrix molt, right? So, but the problem is because GPUs are so like throughput heavy. But 1,000 3x3 molts. Do you have 1,000 3x3 molts? Oh, to create the one matrix molt in the end. Yeah, you're right. You're right. It's 1,000 3x3 molts, and the 3x3 molts are going to be harder. Okay. So yeah, that is a question, and I think you're right, because this one matrix molt is a combination, is a composition, right, of the 1,000 different steps to get there, right? So that's equal to 1,000 3x3 molts. It's close, except for the fact that these are vector matrix molts. Molts. So yeah, no, Vitrevi's right. Because these are vector matrix molts, no matter what, I mean, even if these were matrix molts, which they're not, but if it was, then it would still be faster to do it this way. Yeah, no, I'm fairly certain you're right. So unless there's some fast way to do a composition, maybe because of the redundancies of the functions that we're applying, then this way should be faster. Doing it via the chaos game approach should be faster. So the caveat here is if there's some fast way to do the composition because of, if fast because of redundancy somehow, then we could speed this up. But right now it's looking like it's almost certainly faster to do the chaos game approach, which is good. That's good. That's good to think about. The advantage of the trit string approach, I'm just gonna come back to it for just a second, is that it does span the entire tree, right? That is something that the chaos game might not. There might be redundancy in the locations of the points for the chaos game that you can't account for, whereas the trit string approach will definitely have separate points, but that's not going to matter when you get 1,000 layers deep. What's the function composition for functions expressed? What is a function composition for functions expressed as matrices? I mean, in this case, the function, right, is going to be, it's going to be, I mean, these are all affine transforms, right? So it's going to be one affine transform chained to another affine transform, chained to another affine transform. The answer is I don't know. I really don't. Yeah, I don't know at all. Okay. No, this is good. This is good. This is good. I think though I'm gonna keep to what I said before. I think we're gonna close here. My brain is kind of buzzing with a whole bunch of different ideas, different ways to approach this. I think that will be done tomorrow. I should be streaming tomorrow at 4:00 p.m. I think I have a meeting at from 3 to 4, but I should be able to stream at 4:00 p.m. Tomorrow, and we'll go from maybe 4 to 7 tomorrow for streaming, and we're just gonna start working on some implementations. No matter the case, doing the implementation via the chaos game approach, which we wrote down here, is definitely something we need to do. So that's what we're going to do, and we're just going to show how to make it a bit better. I think that's a matrix multiplication because matrix multiplication is associative, so f of g of x is m of x. Right, no, that is correct. Yeah, no, that's definitely correct. But my question was, like, if you're doing m of x times m of g times, again, m of f somehow, like, is there some way, because m of x is m of f, if you do m1 times m2 or whatever, and then you do times m1 again, is there some way to, you have m1 twice, is there a way to make it so you can somehow cancel something out? I don't know, like, I don't think there is, but potentially there's something that we're missing here, and I'm just dumb, right? So this is a question, right? And I don't know enough about this, so I think we need to look into this. But I'm really happy with this. I'm happy that we sorted out the tritzing stuff. We spent a long time talking about fractal compression, which is super cool. Really excited about that. Really excited to hear that this idea that we had about turning any image into a fractal is actually just another form of fractal compression, and like it's almost certainly going to work. The question is how well it works, and I don't know. Zociliano, thank you so much for following. Really appreciate it. Yeah, this has been really good. I really do appreciate all the conversations here. Let me go ahead and save this for now, and we'll close stream. If you guys have anybody that you want to raid at the end of stream, feel free to let me know. So let me save as, we're going to do projects. Flamify should be in here somewhere, and then we're just going to put it under notes. Where are we? Flamify. Here we are. Notes, and we're just going to say MISC. Sure. Okay. Let's see, who's live and who do we want to raid? We've got, let's see. There aren't too many, Freckled Scientists. Yeah, we do Freckled Scientists. Caitlin V3 is doing Solder Sunday, I guess. I figure you guys probably, let's see, what's Freckled Scientists doing? Subathon, Reaction Diffusion Experiments. How about we do Caitlin V3? Yeah, let's do the raid on Caitlin V3. So let's go start that raid. Raid on Caitlin V3. And yeah, that's good for now. So thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I'll see you guys around next time for the next episode of Simuleos. Should be tomorrow, 4:00 p.m. We're hopefully going to hammer out the next, at least one of these implementations. Maybe talk a little bit about function compositions. I'm pretty sure you guys are right that the regular iterated approach will work best. But, we'll see. Anyway, guys, thanks again, and I'll see you guys next time. Bye, guys.